Recall how, while exploring the microworld, you noticed that all fundamental particles you encountered were always the same. Any two electrons were invariably absolutely identical. How is this possible when, in everyday life, there's no such perfection? No matter what you do, build, or look at, there are never two completely identical objects or people, not even twins or birds or thoughts. Nothing, even if objects appear identical, is truly identical. So, how come all electrons and other fundamental particles are always absolutely identical in their kind? The answer lies in the fact that all elementary particles throughout the universe thrive on the same entities that can swallow them back into the quantum field at any moment. In the vacuum of quantum fields filling the entire universe, all electrons are identical expressions of the electromagnetic field. They don't fly out of it, they propagate within it. The same applies to all photons. Every time an electron becomes real, it awakens from its ghostly lethargy due to a burst in the surrounding vacuum of the electromagnetic field. Similarly, whenever a gluon appears, it arises from some energy borrowed or taken from the vacuum of the strong interaction field. Every time a radioactive decay occurs, elementary particles are ejected from the vacuum of the weak interaction field. The more energy the vacuum possesses, the more elementary particles can emerge from it. Now, we're getting closer to the topic at hand. So, everything seems to behave the same way. All fields appear to obey the same laws. Now, what about gravity? Wherever there is gravity, there's also a gravitational field, although this field is different, at least for now, because nobody knows how it can be quantumized. As you'll see later, nobody knows how to make particles pop out of the vacuum of a gravitational field without causing catastrophic problems. But, hypothetically, if it were possible, gravity would have its own particles that, like in all other fields, would indeed emerge from the gravitational field, carrying its interactions. These particles are called gravitons, although they haven't been discovered yet. Curved space-time still remains the best way to explain the action of gravity. Even without gravitons, and even if it's not quantum in nature, gravity is still a field. Therefore, the total number of fields used by humanity to describe everything known so far is still 4. But why 4? Why should there be only 4 fundamental fields? Why not 1042 or 17,200,008 fields to explain the behavior of nature? What about their corresponding vacuums? Do they just coexist without noticing each other? It sounds strange, doesn't it? Wouldn't life be simpler if there were only one field, just the thing that physicists have always been striving for, a unifying theory that ties everything together? Early on, this captivated their imaginations, but they have yet to attempt to unify the 4 known fields into a single one. Who would rule them all? Although it's easier said than done, the elementary particles of each field are not the same, and one of them, the gravitational field, doesn't have any observed particles at all. The excitation of one field leads to different consequences compared to other fields. They don't necessarily share the same electric charge, and they don't have the same properties in general. For example, the electromagnetic and magnetic fields have a wide range of actions, including attraction and repulsion, while the gravitational field only attracts. The strong interaction field has a very short range of action. Nevertheless, for the creation of an alloy of 2 different materials, you need to heat them. If you did this at a high enough temperature, they would blend into something completely new, a new material combining the properties of both. In terms of field merging, theories could work, but an unimaginable amount of energy would be required to merge the electromagnetic and weak nuclear interaction fields into one. It would require a temperature of around 1,000,000 billion degrees. That's undoubtedly beyond the bounds of what's possible in nature as we know it today. However, it might not have always been this way. Indeed, such an enormous amount of energy existed in the distant past when the universe was younger and smaller. Attempting to figure out how nature behaved back then, Glashow, Salam, and Weinberg managed to unify the electromagnetic field with the weak interaction field, discovering what's now known as the electroweak field. They found that, under extreme conditions, one field could contain two fields that today govern magnetism and radioactivity separately. The next step is to combine this new field with the third known quantum field, the strong interaction field, which governs the interaction of quarks and gluons within atomic nuclei. By doing this, we could create something grandly called the theory of everything. But for its emergence, we would need to expend even more energy. How much more, you ask? Well, it's a staggering amount, beyond imagination. Adding a couple or a few billion degrees doesn't really play a noticeable role. So, how do we know if this is real? How do we know that Salam, Glashow, and Weinberg were right? Besides the sense that having one field is more elegant than three or four, how do we know that a theory of everything is expected to be discovered eventually? Physicists have predicted that when fields merge to create a new one, it should have its own fundamental particles and force carriers. To test this, particle accelerators were built, where existing particles collide with each other. In these particle colliders, particles not only break apart, showing us what they are made of, but the tremendous energy released during the collision also excites all the fields at rest in our universe. The maximum energy achieved from such collisions, as of 2015, corresponds to about 100 million billion degrees. It sounds like an enormous amount of energy, but it's worth remembering that we're talking about particle accelerators that speed up incredibly tiny particles. In practical terms, the energy produced by these microscopic particle collisions is barely stronger than a mosquito's flight locally. However, the energy released is immense. Just as Salam, Glashow, and Weinberg predicted, completely new particles emerged. One of these is the W and Z bosons, particles that make sense only in the context of electroweak interaction. But what role does gravity play in all of this? To turn four fields into one, gravity must play a specific role. So why was it left out? The answer to this tricky question will be the focus of the entire seventh part of the book. Please be patient, as there's much to explore. Now, with all that you've seen so far, you've learned nearly everything you need to, except for one significant topic, mass. You might wonder why you haven't heard about it yet, considering it's quite an important subject. So, where does mass come from? As you know in your heart of hearts, stars create large atomic nuclei from smaller ones. Therefore, stars create mass, not the other way around. In reality, it's the opposite. Stars eject excess energy during fusion processes, and neutrons and protons lose some of their energy. As Einstein's equation E equals mc squared tells us, this creates a source of energy that makes stars shine. You've seen how this happens. However, the equation also tells us something else. If atomic nuclei lose mass due to the loss of gluons, it means that gluons are part of the mass of the atom. In fact, when scientists carefully examined this hypothesis, they realized that the energy of the gluon soup existing inside all neutrons and protons in the universe accounts for not just some, but an enormous portion of the mass of known matter. This energy, contained within all neutrons and protons, is responsible for a huge fraction of the mass of matter as we know it. However, it doesn't account for all of it. The equation doesn't explain why quarks and electrons have mass or, more precisely, how they acquire it. You see, at some point in the distant past, when our universe was extremely young and rapidly expanding and cooling, the electroweak field split into the electromagnetic field and the weak interaction fields. But I haven't told you before that this splitting led to the appearance of another field, another quantum field with its own force carriers. These carriers can't carry any of the forces we've encountered so far, and there are no other forces, so what do? Well, they give mass to certain particles, leaving others massless. For example, photons and gluons don't feel the presence of mass. They can travel through their respective fields without slowing down. However, quarks, electrons, and neutrinos do feel mass, so they can't reach the speed of light. So, how do we know that this is true? How do we know that this mysterious field is responsible for the mass of these particles? Well, like all fields, this new field should have its own fundamental particles. But, as expected, they aren't so easy to see or detect. According to calculations, it would take an enormous amount of energy to wake up the field and make its fundamental particles come to life, even more energy than for the electroweak field. Nevertheless, in 2012, somewhat surprisingly, scientists managed to do just that at the most powerful particle accelerator, the European Organization for Nuclear Research. They discovered a fundamental particle belonging to this field. She was the missing piece of the puzzle. It became known that the origin of all the known mass in the universe, whether from gluons or not, was indeed confirmed. The media call this discovered particle the Higgs boson, although there may be various types. The field responsible for giving rise to it is known as the Higgs field or the Higgs mechanism. British theoretical physicist Peter Higgs and Belgian theoretical physicist François Englert received the Nobel Prize in 2013 for their discovery, which they had predicted over 40 years ago, along with Robert Brout, who unfortunately passed away in 2011. In other words, they discovered that 13.8 billion years ago, when our universe cooled down after the Big Bang, a certain portion of mass came into existence. This was an impressive achievement for them and all of humanity. Despite the sensation it caused, it's important to emphasize that the Higgs field is not responsible for the mass of everything we're made of, only for a portion of it. The majority of the mass of neutrons and protons, as mentioned earlier, comes from the forces that bind quarks within them and create a quark-gluon soup. If the Higgs field were suddenly turned off, quarks would become massless, and we would die, but the mass of the proton and neutron would hardly change. Now that the role of the strong interaction field in our mass is established, when you know where all the mass of known matter comes from, recall all those particles you saw emerging from the vacuum earlier in this chapter. You saw them but weren't supposed to. Nature doesn't allow particles to appear on their own without paying a price, and as you will see now, this price is the existence of a new type of matter called antimatter. Chapter 3, Antimatter. Throughout most of Earth's history, its surface was virtually unknown to human beings. Today, we can easily access images of the entire planet thanks to satellites, but just a few centuries ago, when only small patches of Europe, America, and Asia were drawn on maps, the rest of the world was a mystery to the people living there. They had to leave the safe shores and brave storms and tempests to find out what lay beyond the horizon. One after another, they discovered distant land masses where no human had ever set foot. They also found other civilizations on small territories surrounded by water, which they called islands. Large land masses were named continents. Each discovery expanded the realm of humanity while simultaneously pushing the boundaries of the unknown further away. As decades passed and people ventured beyond their familiar lands, they realized a simple fact. We all live on the surface of an incredibly rich but rather small sphere hurtling through the vastness of space. While writing this book, anthropogenic satellites were sent hundreds of millions of kilometers from Earth to try and determine the origin of water and possibly the building blocks of life on our planet. Humans no longer had to embark on risky adventures. Robots did that for us. However, in the early 21st century, the excitement about interplanetary travel seemed to be rekindled. Could it be that there are still places on Earth, even in the 21st century, that remain unexplored? Can you still be an explorer while staying on Earth and not venturing out into the unknown? Of course, you can. You can explore the depths of the oceans, where conditions are just as hostile to our technologies as they are to our bodies. Much less people have taken steps down there than have set foot on the moon. Or you can have a completely different approach and engage in science. Although science may not be as glamorous as sailing ships or piloted spacecraft, it can take you to places beyond our sight, to places where nobody has ever been before. As you've probably noticed by now, listening to this book may take you to places that are inaccessible to the body, to places where no one has ventured before. No one can anticipate the direction of discoveries, whether they're islands or continents, and many explorers had to face failure to blaze a trail to great discoveries. Success is not guaranteed, but the same holds true for science. The discovery of antimatter follows this ancient path of pioneers, where one person's help can enlighten everyone about the next amazing fact. Our world, the matter-forming planets, stars, and galaxies, is only half the matter. And he did not understand this by pure accident. He relied on what Daniel had done. It's obvious that Einstein's work on how things move, especially when they move very fast, and the curious behavior of quantum particles played a significant role. The man behind this was Paul Dirac. He created quantum field theory and, therefore, discovered antimatter. Dirac was a British scientist who lived from 1902 to 1984. He held the Lucasian Professorship of Mathematics at the University of Cambridge, one of the most prestigious scientific positions in the world. It was held by Isaac Newton from 1669 to 1702 and later by Stephen Hawking from 1979 to 2009. So, what is antimatter? You already know that E equals mc squared, where mass can be converted into energy and vice versa at a fairly high rate. As you saw in the previous chapter, this energy can temporarily be borrowed from the vacuum or fields to create particles. Now, let's go back to the mini-universe. You're still in an empty universe surrounded by a vacuum, specifically the vacuum of the electromagnetic field. Right in front of you, an electron emerges from it. Why? Because it can. You see the appearance of an electron. Just like that, a minute ago, there was nothing but the vacuum. Now, there's an electron. The electron has mass. The mere fact of its appearance means that some amount of dormant energy was converted into mass. The equation E equals mc squared is easy to understand. However, the electron also has an electric charge. So, where did this electric charge come from? Mass arises from energy, and mass and energy are equivalent. So, the emergence of mass and borrowed energy is a balancing process, a simple conversion of energy from one form to another. But electric charge presents a different problem. The appearance of an electron results in a negative electric charge. Until that point, there was no negative charge, but now there is. This is absolutely unacceptable. As I mentioned at the end of the previous chapter, you can't create something from nothing without paying a certain price in real life. But in the quantum world, such things happen. So, what do we do with this charge? We can't just ignore it because there are too many electrons in the universe. Each electron carries a charge, and many other fundamental particles do too. So, where did this charge come from? The simplest answer is often the right one. Here it is. Electrons never appear alone. They must always emerge with an identical particle, except for its charge, which is opposite. What do we call such a particle? It's called an anti-electron or a positron. This concept was introduced to ensure that the total charge of all created electron-anti-electron pairs, at any given time, would be zero. There's no need to invoke E equals mc squared or anything else. This phenomenon doesn't violate any laws. The total charge was zero long before electrons and anti-electrons appeared and continues to be zero. This brilliant insight was made by Paul Dirac. So, what's special about anti-electrons? Particles with opposite charges, but otherwise identical, were unknown until then. Nobody had seen anti-electrons. Today, we detect them everywhere. The process through which electrons and their antiparticles, positrons, emerge from nothing is called pair production. There's also a reverse process. When an electron meets an anti-electron, they annihilate each other, and their mass is converted back into energy in the form of light, a momentary flash. Brass electrons exist on their own. They're all created by the electromagnetic field during their birth. Therefore, positrons must also exist on their own. But you can't find them everywhere. In 1928, Paul Dirac called the anti-electron a hole in the sea of what we now call the quantum electromagnetic field, as it corresponded to the absence of charge. The anti-electron was experimentally discovered 5 years later in 1933. Dirac was awarded the Nobel Prize in Physics in 1933 for his remarkable work on field theory. Anderson, an American physicist, was the first scientist to truly detect anti-electrons and confirm Dirac's ideas. However, instead of calling them anti-electrons, he gave them a new, more commonly used name, positrons. Anderson received the Nobel Prize for his research 3 years later, in 1936. That's how antimatter was born. I've already mentioned that half of matter is antimatter. But if it were just anti-electrons, they wouldn't make up half of the universe. What about antiprotons, antineutrons, antineutrinos, and antiphotons? Some particles don't have a charge and can play both sides, serving as their own antiparticles. A good example of this is light. Photons and antiphotons carry no charge. They are identical. So, why don't we see all the other particles around us? The answer is that they exist. They are all around us, around you, but not in large quantities. This is because they only exist for very short periods of time. Remember that any of these particles, when they encounter their opposite counterpart, immediately annihilate with it, disappearing in a flash of energy, as per the equation E equals mc squared. However, somewhere else in the universe, the entire world could be built from antimatter. If you like, you can call it an antimatter universe. Nobody knows if antimatter universes exist, but if they do, and if you ever happen to encounter someone from there in outer space, don't shake hands. Your antimatter counterpart will turn you both into a bomb, and you will explode spectacularly. Nevertheless, some traces of antimatter are present even within you right now. For instance, during radioactive decay, some antimatter is created each time only to annihilate with its matter counterpart, releasing a powerful beam of light, which usually passes through your body unnoticed. Your eyes can't see such rays because, as we discussed earlier, there was no evolutionary need for your eyes to develop the capability to detect them. But what you can't see, technology can, and clever engineers have turned this discovery into effective medical diagnostic and research tools. For example, PET scanners, which stands for positron emission tomography. Doctors introduce radioactive tracers emitting positrons into your body. During the decay reaction, positrons annihilate with nearby electrons, creating powerful gamma rays detected outside your body by a PET scanner to create 3D images of how your body functions. It's a brilliant technique. Now that you know about fields and their vacuums, about mass, charges, and antimatter, you're ready to travel beyond what you saw in the first part, toward the Big Bang and beyond, to the origins of space and time. So, if I were you, I would take a deep breath before switching tracks. Chapter 4, The Fourth Wall. For many years, without explicitly asking the question, you've unconsciously considered it a given that the universe is mostly empty, static, and unchanging. Unlike our ancestors, you've probably heard of the Big Bang, but you might not have thought about what it really means. In reality, in many ways, we all resemble swimmers, except that, as you already know, we swim in a sea of fields, not water. These fields fill the entire universe, and they are not uniform, rather, They are quite complex. With this thought in mind, it becomes much easier to understand how mass, charge, and antimatter are all intertwined within these fields. The universe is vast, with unimaginably large distances between any two stars, galaxies, and galaxy clusters. But there are no voids. There are only fields that connect distant objects by allowing them to interact through the exchange of particles, the so-called carriers of interactions. These fields never overlap. They connect everything. In this thought, there is something almost poetic and profound. And since you're about to rewind the entire history of the universe back to the birth of space and time, you might wonder if all the drinking, weeping, singing, writing, drawing, and speculating Holy men throughout the ages were onto something. In a sense, maybe they were, but they certainly didn't know why. But our robot supercomputer does know, and it's back on the stage. The bright yellow tennis ball cannon reappears right in front of your face. It still lacks a face, and it gazes at you through its firing tube. But this time, you're wise enough not to see it as a mere mechanism. Feeling strong and inspired by the reliability of all the knowledge you've gained, you prepare your mind for another attempt to imagine the entire history of the universe from nothingness. A metallic voice says, "I'm ready." It informs you that the machine is about to transport you to the origins of space and time. However, the robot doesn't leave any time for your response, and a moment later, you find yourself in the sky above your home, your house. The computer has relocated you from where you were to the sky above your native town. Now, both of you are flying upward like an arrow. You pass through various layers of Earth's atmosphere and emerge into the open cosmos above your home planet. "I'm going to take you on a journey through the best computer simulation in the world," declares the robot, programmed to never conform to previously unraveled laws of nature. Even the most powerful supercomputers on Earth are striving to see what you are about to see. So, onward. I feel the excitement of the upcoming journey, the eagerness to venture beyond the visible, to cross the alternating layers wrapped around the Earth of the past. You know that if you were to travel to the stars in the conventional way, starting on an ordinary morning with your physical body and not through the mind, it would take a significant amount of time. And when you reach your destination, the star won't be the same as it is now. It will change, just as if you wanted to go to New York right now. The journey would take hours, and the New York you arrive at will be different from the one you set out for. Cities, cars, clouds, and raindrops, nothing will be in the same place for long. Similarly, when you embark on a journey to a distant star in a remote galaxy, the difference will be even more pronounced. By the time you reach your destination, the universe will have expanded, and the cosmic microwave background radiation, the relic radiation of the Big Bang, will have cooled down. However, traditional space travel won't get you to the past. So how can computer simulation take you back, and to a distant past at that? The answer is simple: you can find yourself at the moment of the universe's birth, witness it firsthand, without physically traveling anywhere. You just allow time to move in reverse, and that's precisely what starts happening. Without a twitch of your face, you embark on a new journey, a journey backward through the fabric of the universe, to reach the moment of the Big Bang, to go beyond it, from your current location. With surprising sensitivity, the robot computer dims itself, so as not to interfere with your sight. In an instant, you find yourself 7 million years in the past, above the Earth's surface. The cosmic microwave background radiation, a faint glow that bathes the cosmos, is a bit warmer, but 7 million years isn't much in the grand scheme of the universe's 13.8 billion year history. There's not much difference up here compared to a minute ago. However, the Earth beneath you has changed. No cities or megacities, no glowing streetlights. The first humans are just beginning to stand out from their ape-like ancestors. Your distant ancestors are still hairy, hunting wild beasts. Humanity has come a long way. Another leap takes you 65 million years into the past. Dinosaurs have just gone extinct due to a combination of massive volcanic eruptions and a catastrophic asteroid impact, leaving behind only small mammals. Some of them, through a series of evolutionary steps, will eventually become your hairy ancestors. Then there's another jump, 4 billion years into the past, just after a planet the size of Mars collided with Earth, biting off a piece to form the Moon. The relic radiation is getting warmer, and the surface of the last scattering is getting much closer. The visible universe has shrunk to less than 70% of its original size. A few billion years before your existence, you're transported again, 1.5 billion years before your birth, or 13.7 billion years ago. The visible universe is now less than 25% of its original size, and the last scattering surface is very close. Galaxies are forming around giant black holes, sometimes leading to collisions. You're only 5 billion years away from the Earth's formation, or 1.5 billion years before you came into being. The visible universe has shrunk to less than 2% of its original size. You're in the Dark Ages, the same Dark Ages you traversed in the first part of the book, but this time it's different. These Dark Ages are cold and dark because you've arrived when the Earth was visible in 2015, over 13.7 billion years after the Big Bang. However, 13.7 billion years ago, everything wasn't cold and dark. And now you're right there. The first stars haven't ignited yet, so none of the visible matter has formed through nuclear fusion in stellar cores. You're surrounded by the tiniest existing atoms, mostly hydrogen and helium, and the brilliant light that initially filled our universe. It's a bright light everywhere, a light that became microwave radiation much later, after billions of years of cosmic expansion. And then, another leap, 100 million years further back, 12.8 billion years ago. The last scattering surface is just a light minute away, meaning the visible universe is only 1/8 the distance that separates the Earth from the Sun. The entire universe is transparent, and it's a hot 3000 degrees Celsius everywhere. You're still in the Dark Ages, but everything around you shines so brightly that you wonder if the chosen term really suits it. You pause for a moment, and the computer instantly begins to rewind time a bit further. In slow motion, you find yourself in a strange, literally invisible place, 1 minute back in the past. You start what sounds like the last journey on the surface of the last rush is not right in front of you. You take a deep breath, ready to cross over, to go beyond the wall, to reach the invisible. Time continues to rewind, and there you are, beyond the wall. You've entered a part of the past universe that has never seen the light. You really can't see anything anymore. Light doesn't propagate here, there's just too much energy. But you know what to do. You immediately switch to yoga techniques and realize with astonishment that the universe beyond the just crossed surface is vast and ancient, at least 380,000 years old. Your journey is far from over. You focus again on what's happening now behind the wall at the end of the visible universe. The temperature of the surrounding environment is 5000 degrees Celsius. All electrons that once started binding free atomic nuclei to become hydrogen and helium exist here on their own. Photons collide with them, exciting them before the radiation sends them back to collide with another electron. The electromagnetic field is so filled with energy that all its fundamental particles transform into each other almost instantly. In a flash, you find yourself at least 1,000 years before the universe became transparent. You are surrounded by a dense broth of particles representing a mixture of all quantum field excitations, their elementary particles, and carriers of interaction. Everything collides with each other, leaving no room for anything else. There's too much energy all around. Everything appears, collides, and disappears. Meanwhile, time continues to rewind. The universe is still contracting. The energy density is increasing, and the conditions are becoming more and more extreme. Nevertheless, you try not to get lost and focus on your journey back in time. Your consciousness and yogic methodology make it look like a very realistic simulation. The universe keeps contracting, and the fabric of space-time is bending monstrously. Nothing you know or can imagine possesses such destructive and distorting forces for just a fraction of a second. You wonder why you don't feel more gravity at this stage, but you don't have time to think about it. You've traveled back in time by several thousand years, and now you're surrounded by unimaginable chaos. Your virtual heart starts pounding harder and harder as the temperature, pressure, and gravitational influence on the visible world around you reach incredible levels. Now you're 380,000 years before the universe became transparent. If you were to look through a telescope on Earth right now, more than 13.8 billion years ago, you'd be hundreds of thousands of light years beyond the boundary marking the limit of the visible universe. Looking in the opposite direction, you're practically 3 minutes away from what could be called the birth of space-time. Time continues to flow in reverse. Even atomic nuclei are breaking down, allowing all the quarks, neutrons, and protons to move freely at their own discretion. Strong nuclear interactions engulf the surrounding energies. Protons and neutrons themselves, the stable structures, even begin a frenzied dance in which quarks, created from carriers of interactions, are knocked about. Astonishingly, protons transform into neutrons and disappear from the universe surrounding you, with a temperature of 100 billion degrees everywhere. But you don't stop. You continue moving through time. Second by second, as time ruins, all the surrounding particles of light transform into pairs of matter and antimatter. Everywhere, it seems like the last moment is as numerous as the previous ones. So how did one of them eventually become predominant? You're in a trance, trying to understand how the balance was disrupted. Something extraordinary must have happened here, a mystery that might even be uncovered this year or the next when the upgraded and more powerful particle collider at CERN, relaunched in June 2015, begins to unravel it. You'd like to linger here a bit longer to clarify it for yourself and report it to Sir, but you're not in command anymore. You're rushing through a universe filled with a soup of such immense energy that everything around you cracks. Gravity warps and breaks everything. Fields are excited to levels beyond reason. It's not the weight of a star that makes gravity manifest by curving space-time. It's the energy of the entire universe, squeezed through a sphere with a diameter of 100 light-years. Such a sphere, at its center, could contain no more than 5,000 stars, whereas it contained the energy to form hundreds of billions of galaxies, each with hundreds of billions of stars, not to mention. Nevertheless, no matter how you prefer to consider everything around you, you continue to fly against the current of time. Now you're just 1/1,000,000th of a second away from the final destination. The temperature has reached 100 million billion degrees. With such an enormous amount of energy around, even the guards of quark prisons, gluons, can't hold their prisoners. Neutrons break down, and quarks, now free, begin to interact with their anticopies, transforming into pure energy. Looking around, you realize that discussing the difference between matter, light, and energy is now entirely redundant. Fields that were independent entities throughout the journey from Earth here are now merging as expected. The electroweak field is particularly active since some familiar particles you're used to seeing everywhere are disappearing. New fundamental particles belonging to the electroweak field are emerging from all sides. The Higgs field disappears, along with the Higgs boson that had long remained hidden from human knowledge. The particles you now see are the W and Z bosons, carriers of the electroweak interaction. The energy around these particles is so intense that they're created with great difficulty on Earth, but here they are everywhere. The universe is now heated to 100 billion degrees, and the laws of nature are notably different from what you've known throughout your life. Quarks and antiquarks are annihilated by background radiation. 1,000 billion billionth of a second after what could be considered the source of space-time's origin, an event we might call the beginning of all beginnings, takes place. You've just reached the location of the Big Bang, where the accumulated energy in the unified field begins to transform into particles. Surprisingly, despite experimental physics never having reached this point, the computer seems unwilling to stop. First and foremost, it wants to show that the history of the universe doesn't begin here. To your great astonishment, while time continues to rewind, all matter and energy of the entire universe suddenly vanish. Contrary to expectations, everything rapidly cools down as all available energy transforms into another field, one you haven't encountered before. It's filled with its own particles and is called the inflaton field, believed to be responsible for the initial expansion of the universe. As the universe cools down, all the constituent fields that make up our universe now merge into one great unified field. Only gravity remains separate from this unification. Being so close to the beginning of beginnings, you start to think that not much more is left to happen. In reality, you've just reached the place that has been called the Big Bang, the moment when the energy accumulated in the unified field begins to transform into particles. However, it turns out that the concept of space and time you've used so far no longer applies. Gravitational space-time curvature is too extreme, and quantum effects occur without space or time. Traveling further is impossible and meaningless under these circumstances. You haven't reached the true beginning, and you have no idea how to devise a way to get there. It's frustrating, and suddenly, you want to look at everything from the outside. Up until now, you've always remained inside the universe. However, the concept of the outside now seems equally meaningless. What you're standing on is the surface of two walls, significantly different from the surface of the last structure that limited what you could see from Earth. This wall is impenetrable, not to light but to modern knowledge. Behind it lies the realm of quantum gravity, where all known fields of nature can be unified through quantum means. The universe becomes an enigma here, intertwined with the sciences of the 21st century, faith, and philosophy. In a sense, this is where our knowledge stops, replaced by purely theoretical research for journeys beyond the surface of the last structure. You can't use telescopes that collect cosmic radiation here. But scientists have built an accelerator of elementary particles that allowed them to reach temperatures and pressures they expected to find beyond the universe. And it worked. Scientists have discovered new laws and have managed to swim back in time, albeit indirectly. As you read these lines, they have already constructed and continue to create next-generation telescopes to detect not just radiation but gravitational waves. The pulsations that propagate through the very fabric of space-time. Such telescopes can detect signals emanating from beyond the surface of the last structure, from that distant past where you have just been. However, traveling beyond the wall of quantum gravity, also known as the Planck wall, is an entirely different matter. No one is sure how to think about what lies beyond it. The visible universe was so tiny back then that to comprehend it, you need a theory about something extraordinarily large, compressed to minuscule dimensions. In this theory, quantum laws, with their quantum leaps and more, apply to the universe itself. It requires quantum gravity, among many other things, and we don't have it. We don't have the research frameworks, so you can't go any further. In fact, you can't even speculate about what lies beyond the Planck wall. It's not in space, it's not in time, as these two concepts have no meaning there. When scientists say the age of the universe is 13.8 billion years, they mean that 13.8 billion years have passed since space-time gained meaning. This happened approximately 380,000 years before the surface of the last structure, or 380,000 years before relic radiation filled cosmic space. This moment occurred mere million billion billionths of a second before the Big Bang. Ultimately, Scientists can rightfully say that this is the amount of time that has passed since the emergence of space and time. But it doesn't mean that our universe was born then, just as it doesn't mean that it's the only existing universe. You find yourself back in your living room, on your worn-out old couch, profoundly affected by having traveled through space and time, witnessed galaxies, stars, fields, and the influence of gravity on the shape and destiny of space-time, dependent on the universe's contents. Up until now, you've made it here, and something incredible is happening with you. As you stand on the verge of a stunning revelation, thoughts race through your mind. You feel like a child again, discovering that the world can be understood, realizing that you've died somehow before, at some point. It's clear now, and the computer has shown it all to you. You've learned from Einstein's theory of relativity that you could ascertain the history of the universe from beginning to end by knowing only what's contained in it. Now you know that the contents of the universe consist of quantum fields, moving, evolving, and interacting among themselves. There are more than 3, at least as of today, but they were once unified, a very long time ago. These fields are the parents of all particles and antiparticles in the universe. The reason why all elementary particles are the same, whether they are inside your body, in any other galaxy, in the past, or in the present, is now clear. It can only mean one thing: you've become like a god given. You understand gravity, you know it's inside the universe. Connecting these 2 dots together, you gain knowledge of the entire history of the universe and of its past or present future. You're almost a god, at least by definition. A smile lights up your face. You immediately grab your phone, dialing the only person you can remember at this moment. Who is it? A voice on the other end sounds suspiciously like your second cousin. It's me. Hi, how are you? You exclaim. Better, she replies. I feel amazing. Well, you say, it's nice to hear something happened. I traveled, explored the universe, you explain. Oh, well, she says, I know it sounds silly, but I can create and develop a universe like ours, just using my imagination. It must be like feeling like a god. Grandma pauses. I see, she says. Do you understand gravity? Do you know it's inside the universe? Maybe you've found something where you could apply your knowledge of ballistics or any other laws of nature? Are you talking about initial conditions? You ask. Yes, I am, she replies. They know you have something you could apply your ballistics or any other laws of nature to. You could ask Katya and Gabby to call you so that you could talk to them about it. They really understand these things. No, there's no need for that, you say. All right, she says. Will you call me back when you find your initial conditions? Yes, you reply. Thanks for the call, dear. Goodbye, she says, and she hangs up. As you stare in puzzlement at your phone, you hear the following words. Let me tell you the following. As you probably understand, she is right. To comprehend something about the universe, you need 2 types of data. The first is a set of laws, and the second is initial conditions to apply those laws to the universe as a whole. To know its entire fate from a clean slate, you need impeccable initial conditions, a state to which you can apply the laws of evolution. However, you simply don't have them, and what's worse is how can you be sure that the laws of gravity and quantum fields you've discovered are applicable from the very beginning of the universe? With a sigh, you sit back on the couch, holding a cup of coffee, feeling that some crucial information is still missing. Chapter 5, Lost Pieces of the Past Everywhere in Space-Time. Space-time, what more is there to discover about it? What haven't you seen yet? Particles, carriers of interactions, fields, gravity, haven't you experienced them to understand why you feel so anxious? You open your eyes, and to your surprise, you're no longer at home. You're sitting in a cramped seat in a strangely familiar airplane. Your seat is 13, and, to be precise, the other passengers are queuing in the aisle, preparing for disembarkation. In confusion, you peer out the window, and there's no doubt. You've truly returned to your future flight, which has just landed in the year 2415. Struggling to grasp the situation, you stand up and follow the other passengers to the exit, slowly regaining your senses. Amidst long, seemingly infinite glass corridors with a view of the sea, you wonder how you got here. Just a moment ago, you were at home. You had just called your second cousin at the end of your journey across the known universe. You remember that around Earth, there's a sphere with a radius of 13.8 billion light-years, containing all the past of humanity, which can be reconstructed using relics. Beyond it lies another layer of reality, existing 380,000 years ago, and no one knows what's beyond it. As you continue walking through the ever-expanding corridors, the bright sun of 2415 bathes the Earth below in its rays, reaching it in just 8.3 minutes. A deep sense of loneliness suddenly engulfs you. What's the point of all this? How can our universe be so vast? We're so tiny, doomed to get lost in space and time, tormented by the awareness of this fact. Or are we humans at the beginning of a long journey of technological progress that will someday make distant worlds and perhaps even the near ones indistinguishable? Is this where it's happening, and you're on the brink of seeing one of those many possible futures? Futures where the past and future are merely directions of movement for our descendants. Time travel has been a human fantasy for centuries, but you've never heard of anyone who actually achieved it. Once, Stephen Hawking threw a time traveler party at noon on June 28, 2009, just to make sure that only time travelers attended. He only sent the invitations after the party, but nobody showed up. So what does this new adventure mean to you, to a being without any significance, lost in the vastness of space and time? The winding glass corridors you're walking through eventually lead you to the hall of a massive airport. It might be more accurate to call it a time port. Hundreds of people queue up to pass through something resembling customs. The hall is very brightly lit, with light streaming in through giant windows overlooking skyscrapers rising from the sea. How did you end up here? The sudden reality of being back troubles you. If this is real, then what happened to your past? If you've truly traveled 400 years from takeoff, then your past is still out there somewhere. Can you return to live out that past life, or is it lost forever? As you contemplate these thoughts, you almost feel the insurmountable chasm that separates you now from all your loved ones. Sadness tugs at your heart. But in what you've seen so far, there's a certain consolation. The past lives of your loved ones have become a sequence of images moving through space-time. All light and other massless particles, even those that bounce off or interact with their bodies, have created a memory of their existence. Some image, like a projectile hurtling at the speed of light away from Earth toward the distant, unknown pulsations of invisible but omnipresent fields. And since you've traveled 400 years into the future, the visible memory of their lives washes over the surface of planets and stars located 400 light-years away from Earth. Their image will continue to move, spreading farther, possibly occasionally encountering some alien collecting device until the universe exists. There are speculations about what constitutes us, matter, and the atoms that were born billions of years ago. A gift long gone from dead stars before coming together to form your friends and loved ones. All their billions upon billions of particles have now scattered across the world. You might even be near one right now. Perhaps we're not as insignificant in the grand scheme of things as you think. You ponder as your imprint here remains, growing and not vanishing. It's comforting to know that the memory of our lives will always exist as we travel among the stars. Time, space, and fields connect us all in an immensely vast reality. As you stretch your arms out to feel the forming warmth and raise them high into the air to see the unseen slope created by Earth and its surrounding space-time, You begin to understand how all scenarios of the past, present, and future can truly be interconnected. Everything is in order with you, sir, a woman in uniform asks, pulling you from your thoughts. A bit flustered that you didn't notice her approach, you manage something like, "Thank you, I'm fine." But some things in life don't change, not even in 2415. Everyone immediately feels a bit guilty when confronted by well-trained customs officers. "Where are you from?" she asks, snapping you out of your reverie. "From the early 21st century, you reply, trying to give your voice as everyday an intonation as possible. "Please follow me, sir," she says in a tone that leaves no room for negotiation. While almost all other arriving passengers nearby shoot you disapproving glances for causing problems, you follow the officer through a corridor until you reach a door. "Please come in," she says. Inside, you find another rather unfriendly-looking officer sitting behind a large desk. Above his head on a big sign, it reads Psychological Decompression Unit for Time Travelers. "Any aggression towards our staff results in immediate consequences," he says impatiently, pointing to a chair opposite him. "Don't look around. The room is empty except for the desk, unfriendly officer, and the familiar yellow tube peeking out from behind the desk. All your worries instantly vanish as soon as you acknowledge your companion's presence. And what's more, computer simulations ask if it made you feel a little better. To understand your place in the universe, to ponder the nature of life and death. The quest to understand reality is, after all, a profoundly personal one, and not something supercomputers should impose on you. Your right to have your own day is still yours. Nonetheless, I must caution that, until now, you've merely skimmed the surface of both theories used by scientists to describe the universe, quantum field theory and Einstein's theory of gravity. Of course, both seem logical and elegant, but you should know that there are problems with many concepts associated with them. In truth, no one really understands the universe entirely. Even the reality around you right now, whether on the couch or on a tropical beach, is shrouded in mystery. But one thing can be said for sure. All mysteries, whether they lie around you, within you, or far beyond the Big Bang, ultimately lead to the unification of quantum fields using quantum gravity theory. And although, to be perfectly honest, such a universal theory is unknown, at least one property of quantum gravity has been discovered. The key, as you seem to like it, is the tantalizing hint at what lies beyond the Planck wall. That's good news. The bad news is that there's only one known window that this key can open. Through it, presumably, you will one day travel, even if only in your mind, beyond the boundaries of the beginning of space-time. That's why the robot is here, to take you from the time port. The room you're in disappears once more, replaced by a nocturnal landscape of deep space. You begin to ask the robot where you're going, but they cut you off mid-sentence. "I'm taking you to a black hole," the machine announces. Since you've already been to one at the beginning of your cosmic adventures, you might ask what you missed during your first visit. The answer, for once, is quite simple: you weren't close enough. Part 6, Unexpected Secrets. Chapter 1, The Universe. If you think about it, there's something special about the universe we belong to. The name universe comes from the Latin word universus, which means turned into one. The universe itself emphasizes the rather specific issue it raises. Any experiment conducted within our universe can be repeated multiple times. Want to test Newton's law of universal gravitation on Earth? Shoot an arrow and, unsure if you've understood it, shoot it again and again. With patience, you'll see that, knowing the initial position, angle, and velocity, you can predict where the arrow will land. That's all ballistics is, after all. And it works. Otherwise, long bows and arrows would have long since been abandoned, and England would belong to France. So, by knowing the laws, initial conditions, and demonstrating rigor, you can predict where the arrow will land and defend the whole country. For the universe as a whole, this is a bit more challenging. Even if you had a law that explained everything and applied everywhere, how would you make it work? How would you use it to predict how the universe we live in today became what it is? To do that, you would need to know the initial conditions, which we don't have. But you could try to outsmart nature by rewinding time backward from today. Maybe, someday, you'd reach the initial event that occurred not too long ago. That's precisely what scientists did, what you were doing in part 5 of the journey when you reached the Planck wall. The Planck wall is a good starting point because it corresponds to the moment when space and time became what they are today. But it doesn't eliminate the disturbing fact that, unlike the arrow experiment, you have only one universe. You can't create a second one with different initial conditions to see what comes out of it. At least, not in the lab. But what if our universe is not the only one? What if we were part of another multiverse different from the one we encountered at the end of part 2? Could our reality be just one of many possible realities, each with different beginnings and perhaps even different laws? This hypothesis about such a multiverse is a question you'll soon have to grapple with because it's part of the answer crafted by modern theoretical physics. In the coming parts, you'll experiment with mixing gravitational and quantum theories, something you haven't done before. Mixing gravitational and quantum physics means blending the micro and macro worlds. To prepare your mind for this, you'll have to jump back and forth in both directions like you would in a gym to get your body in shape. By doing this, you'll see that something isn't quite right with the theories you've explored so far. Until now, you've been familiarizing yourself with the theory of relativity and quantum physics separately. But in this part, you'll aim to combine them. To do so, you'll accompany the robot to a place where both gravitational and quantum effects are at play. Now, let's delve into the mysteries of modern science together. Only you and I can claim that there are 3 types of mysteries in physics: theoretical, observational, and the ones that no one can figure out anymore. Black holes and the physics of space-time fall into all 3 categories. They are both bridges and barriers between us and the holy grail of modern research, the theory that unifies the quantum world and the dynamic aspects of space-time discovered by Einstein. That's why the robot intends to take you to a black hole. But why a black hole and not the origins of the universe? Because, in both cases, a tremendous amount of energy is confined within a relatively small volume. In both cases, gravity and quantum effects cannot be ignored. In this sense, black holes and the birth of the universe look remarkably similar, though, of course, no one can look at the universe from the outside through experimental means. Even if we had a law governing the behavior of everything visible and invisible, we couldn't test if different initial settings would lead to evolutionary models for the universe as a whole. We can't create a Big Bang in laboratory conditions, and we can't observe new universes forming in the night sky. This is why black holes are useful. Take almost any galaxy in the universe, and you'll likely find a supermassive black hole at its center. There may also be several smaller ones scattered about. As of 2016, the largest discovered black hole is 23 billion times the mass of the Sun and is located approximately 12 billion light-years away from us. It was very young when it emitted the light we detect today. On the other hand, theoretically, even the smallest black holes can be measured using the so-called Planck unit system. This system considers both gravitational and quantum characteristics in a digital expression. The Planck length corresponds to approximately 1.61 x 10⁻35 meters, an incredibly tiny length. This means that black holes can come in almost any size. Both black holes and the very young universe share some important common features. They both have boundaries beyond which gravity cannot be used without including quantum effects. This boundary is the Planck wall, which we encountered when traveling back in time beyond the Big Bang at the end of the previous part. The moment of the universe's birth is an event that existed everywhere. As for black holes, typically hidden from view, there is only one path beyond their gates, the event horizon. You'll cross it at the end of this part, and this journey will serve as the key to unlocking the seventh part, where you'll embark on the final exploration of the universe from the perspective of the most popular modern theories, a theory of everything, as it aims to unite spacetime and quantum fields. These theories are known as string theories, and they are quite mind-boggling, combining multiverses, parallel universes, extra dimensions, and more. At first, you might think that scientists have truly gone off the deep end. Still, after everything you've experienced, you might find it amusing to discover that much of the physics of the 20th century left us with deep, dark unknowns. However, don't be disheartened. These unknowns are not opaque barriers to scientific progress. They are open windows to the science of tomorrow. In fact, in less than a century, humanity has gained an understanding of nearly everything, and the puzzling ideas emerging in the minds of theoretical physicists today hint at upcoming revolutions in our understanding of the universe. Some of these ideas are ripe for fruition, while others await the right experiment to fill our minds with the promise of a magical new reality. So, what's going to happen to you? First, you'll take another look at quantum fields filling the universe and see that, despite all I've said so far, they still don't make much sense. Then, you'll revisit all the particles of these fields in the context of quantum gravity, discovering that not everything is as meaningless as it might seem. You'll encounter Schrödinger's cat, simultaneously alive and dead. Finally, after being inspired by these breakthroughs, you'll hear about parallel universes branching off from ours like tree branches, realizing that the quantum world lies beyond what common sense tells us about reality. Now, you'll be facing unfamiliar territory. You're heading into the unknown, ready to overcome the gap between the micro and macro worlds. You'll look at Einstein's theories, galaxies, and the universe's expansion again, hoping to find clear formulations. Surprisingly, you won't find them. You'll see that most of the universe's content is not only invisible to telescopes but also unknown. The universe, on both macro and micro scales, is filled with mysteries wherever you look. You'll also need to digest the fact that no matter how powerful it is, Einstein's theory of relativity remains incomplete concerning the warped spacetime. In certain places inside our universe, it cannot be applied. This means that to fully explain everything, we need to find a more complete theory. You might have guessed that you'll encounter these limitations inside black holes and somewhere along the path within the Planck wall. So far, you've been traveling through the best theories ever created by humanity to describe the world around us. In practice, this means that you now know as much about the universe as an average graduate student at one of the world's top universities, perhaps not in terms of technical education, but certainly in terms of familiarity with hypotheses. This is more than enough to become the star of any party. Now, it's time to move forward and see what doesn't work. When you do, you won't just be a star. You'll leave your friends scratching their heads. Chapter 2, Quantum Infinity. Do you still remember what the cosmic vacuum really looks like? What you thought was emptiness has turned into a frenzy of pulsating fields. This pulsation happens because particles are constantly emerging from the vacuum and re-entering it. In the quantum world, if something is possible, it will definitely happen. So, for a moment, forget about your ordinary everyday size and the influence of gravity. Instead, picture yourself as a sports referee, observing two electrons interacting with each other. It's like watching a tennis match where the players are electrons and the balls are virtual photons dancing between them. One electron is somewhere on the right, and the other on the left. They are absolutely identical, both having the same electric charge. As magnets, they should repel each other. It's intriguing to watch them. Right now, the electrons are far apart, moving through the electromagnetic field generated by your electromagnetic chair. They are getting closer and closer to each other. They are on the verge of a collision, but it doesn't happen. Instead, they interact through virtual photons emitted from the electromagnetic field, deflecting each other. Then, as quickly as it began, the game ends. The electrons and virtual photons vanish. You wait for the next game. Another pair of electrons appears. Once it became clear, you decided to focus on virtual photons rather than electrons. You pay attention to your mini-electron class as they move, getting closer and closer. Then, suddenly, virtual photons appear to avoid missing anything. You slow down time. The electrons are in the process of deflecting with the virtual photons. Everything seems fine, but something strange happens. One of the virtual photons that appeared between the two electron tennis players unexpectedly changes. It becomes a pair of particles, an electron and a positron. You cast a quick glance at the electrons, curious about how the loss of the virtual photon might affect them, but it seems they haven't noticed it at all. You shift your focus to the newly formed pair, which is no longer just a pair but 2.5. You squint and rub your eyes, thinking it's a joke. You open your eyes again, and suddenly, thousands of pairs of particles and antiparticles appear between the two electrons. You blink, and it's already millions. Then billions. You blink again, and it all disappears. You check the electrons. They've scattered, just like the previous pair of players. Amazingly, you've just witnessed one of the consequences of quantum laws applicable to the microcosm. In the quantum world, if something is possible, it will happen, and this extends to virtual photons diving into the energies of moving electrons, transforming into virtual particle-antiparticle pairs. These, in turn, can become more pairs or annihilate into light. The possibilities are endless, as infinite pairs of virtual particles can be created. As you contemplate all of this while comfortably sitting in your referee's chair, you await the next game to witness the fireworks. But there are no more players. No electron flies by. However, now that you know what to look for, you see virtual pairs of particles and antiparticles appearing just as before, albeit at a slower pace. They resemble tennis balls, bouncing into existence from nowhere in the absence of players. This phenomenon is known as vacuum quantum fluctuations. They are always present but become much more excited when there's available energy for them to utilize, such as the kinetic energy of flying electrons. Suddenly, an electron-positron pair appears, then they annihilate, spontaneously turning into another pair, a quark-antiquark pair. One of these quarks emits a gluon, which, even in the vacuum where it seems like there's nothing to interact with, must always account for all the infinite possibilities of particle-antiparticle creation and annihilation. These possibilities are so important and numerous, in fact, infinite, that there must exist an infinite amount of energy in every point of our universe, even where there's nothing. Or else the universe would collapse immediately due to excessive gravitational influence on space-time. To deal with these infinities, quantum field theorists came up with a clever trick. They simply decided to forget about gravity altogether, removing it from the equations. While doing so, they successfully removed infinities along with it and performed calculations with what was left. It worked like a charm, as demonstrated by the remarkable Dutch physicist Gerard 't Hooft, one of the brilliant founders of these mathematical operations, who won the Nobel Prize in Physics in 1999 for his work. Thanks to him and other scientists, despite these mathematical tricks, quantum field theory has become perhaps the most successful scientific theory of all time. Eliminating infinities led to predictions of particles that hadn't even been observed yet, and these predictions turned out to be accurate. However, this trick leaves us all somewhat frustrated because it doesn't help to wash down even 1,000,000 mugs of beer at the bar. But why do these infinities occur? Could they just be a result of our ignorance about what's happening in the realms of our universe that are even smaller than the text? The theories exploring them suggest that maybe so. In any case, one extraordinary American physicist, Kenneth G. Wilson, thought that such mind-boggling scales might actually be the problem. He proposed that there was no need to delve into ever smaller scales to speak about particles, just as we don't need to know about atoms when comparing apples at a market. He believed that what's unknown can be estimated and classified and then forgotten. This approach worked, and in 1982, he received the Nobel Prize in Physics. Wilson's idea solved the problem of what happens at infinitesimally small scales without requiring an infinite number of procedures to get rid of infinity. This process is called renormalization. As I've mentioned before, it's quite efficient from the top down to conduct calculations. But you can't hope to ever understand everything by simply skirting around the unknown. You need to delve into it. This is especially true when it comes to the gravitational field, where perturbative renormalization doesn't work. Quantum field theories deal with the contents of the universe, and they are highly accurate, remarkably so. However, their accuracy holds only when they leave space-time behind individually. When they are pinned down, and gravity doesn't exert any influence, it becomes less realistic. Finding a way to reintroduce gravity and turn it into a quantum field is a challenge tackled by quantum field theories. Quantum field theories assert that since fields exist everywhere, they can create small portions of energy or matter called quanta. The elementary quanta of the electromagnetic field are particles with the smallest electric charge, photons and electrons. Similarly, for the strong nuclear interaction field, quarks and gluons become the elementary quanta. When it comes to the hypothetical quantum field of gravity, the previously mentioned gravitons are considered the elementary quanta. You've already heard about gravitons in the previous part, but we ignored them back then. Why are they resurfacing now? Because we want to explore what happens to them. So, let's assume that gravity arises as a quantum field, just like all the other forces. In this case, gravitons become the carriers of this interaction. If one were to calculate on paper how gravitons could affect their surroundings, theoreticians would find their influence to be similar to the curves of spacetime on paper. They would be gravity in its mathematical form. This seems promising, but when scientists think further, they realize that these graviton quanta would entirely undermine the theory of gravity as we know it. Here's why. Firstly, gravitons have no reason not to interact with each other. They exist, so they must be subject to gravity just like everything else and therefore interact with themselves. Secondly, being elementary particles of a quantum field, they must emerge from the vacuum of their own field, leading to the same kind of infinite trouble we tried to avoid with previous field theories. The procedure of perturbative renormalization, which worked before, fails to remove these gravitational quantum infinities. Here, the mechanism of renormalization falls flat, and the standard approach doesn't apply because it ignores the distance over which gravitons act. As a result, truly problematic infinities emerge when attempting to turn gravity into a quantum field in the usual way. It's apparent that you can't ignore gravity to get rid of gravitons, because they represent gravity itself if gravity were a quantum field, as previously discussed. If gravity was a quantum field, as just mentioned, then spacetime should react, encountering infinities and almost collapsing, which doesn't happen. So, oddly enough, despite all the challenges listed, many scientists, including myself, will talk about gravitons as if they exist, at least as part of the grander theory that everyone is in search of. Now that we've broached the subject, let's dive even deeper so you can see several reasons why Einstein's general theory of relativity and quantum field theory diverge. Gravity has a connection to spacetime. In other words, they are intertwined. Quantum field theories, stemming from the vacuum, give rise to elementary particles, thus generating the field itself. Consequently, for quantum field theories of gravity to work, elementary particles should also arise from their own field, but now as spacetime particles. Thus, particles themselves must consist of spacetime. This means that substantial portions of spacetime must surround us, and they can't be continuous. Worse yet, these portions of spacetime must have the ability to simultaneously behave as waves and particles, subject to quantum tunneling and quantum leaps. Good luck trying to visualize that if you're a normal human. Even trying to think about it can make your brain melt. Nature, however, doesn't seem to have a problem with it. The real problem is that even if you forget the infinities, all other quantum field theories, which are advanced in describing everything we're made of, only work as long as there are no substantial portions of spacetime around. In other words, the problem lies in the different conceptions of spacetime between general relativity and quantum field theory. This problem is monumental, with no obvious solution, which leaves you with the curious feeling that you're stuck somewhere in the middle. Humanity has developed two extremely effective theories. One describes the structure of the universe, Einstein's general theory of relativity, which deals with gravity. The other theory pertains to the contents of the entire universe, quantum field theory. These two theories refuse to communicate with each other for a very long time. Even physicists working in each of these fields behaved similarly. They didn't talk to each other. The American theoretical physicist Richard Feynman, a Nobel laureate for his work in quantum field theory and one of the most brilliant scientists of all time, wrote a notable letter to his wife, explaining this attitude. He said, "I get nothing from meetings like this. There are no experiments, so this field is not an active one, so only the very best minds do it, and so there are lots of experts around. This, to my horror, is having its effect on me. Remind me not to go to any more gravity conferences." Nevertheless, thanks to new technologies and the work of theoretical physicists like Stephen Hawking, scientists soon realized that they couldn't ignore what they didn't know. Ideas from both sides began to be exchanged, giving rise to crazy hypotheses that we will explore in the 7th part of this series. Chapter 3, To Be or Not to Be Simultaneously. Do you remember those quantum particles that the robot was playing with in the white room with the metal pillar down in the micro-world? These particles indeed take all sorts of impossible paths to get from one place to another, from one time to another, as long as no one observes them. So why don't all the quantum aspects of everything around you turn you into a quantum being? Wouldn't it be cool if all the different life scenarios you could imagine happened simultaneously? You could be both very rich and very poor, a family man and a bachelor, happy and sad, Nobel Prize winning and born mute, living here and there, now and then. You could truly live all the lives you ever dreamed of and all those you didn't want. But it doesn't seem to work that way. You're made of quantum stuff, right? So why isn't it like that? Well, nobody knows. In fact, this is connected to one of the greatest mysteries of the quantum world. Why don't we see quantum effects all around us? Given that we're made of quantum particles and quantum fields, just like everything else, why do we perceive the world the way we do? They behave like particles on a tiny, subatomic level, which is essentially saying that physics doesn't exist to challenge its own laws, but to attempt to decipher them. However, there's a little problem with that modest statement. The laws of the quantum world are so different from our everyday reality that there must be some kind of transition between the quantum and classical worlds. This is often referred to as the measurement problem. Particles behave very differently when they are not being observed. And this raises the question of how and when quantum systems make the transition from behaving like waves of probability to behaving like classical, definite things. Imagine yourself, smaller than an atom, approaching a particle as it comes toward you. You know nothing about its size, location, or velocity. You only know it follows the laws of the quantum world. You pull out a mini flashlight from your pocket, ready to shine it on the particle, expecting its light to bounce back to you, revealing its position. But to do this, you can't just use any light. You have to use the right one. See, light can be thought of as a wave, and the right light means that the distance between two successive wave crests should be roughly the size of your target or smaller. If you choose a wavelength that's too large, the light won't even notice the particle. It'll pass through it like radio waves passing through your house's walls. However, if you pick the right wavelength, the light will reflect, and you'll be able to determine the particle's position accurately. At the same time, you can also check its velocity. Using the appropriate wavelength of light, you shoot a pulse, and it hits the particle up ahead. The light bounces back, providing you with information about the particle's speed. You can find out everything you want to know. Simple, right? You turn the knob on your ultra-modern mini flashlight to give it a very powerful pulse. You aim and shoot, bam! You hit the particle right on target up ahead. The time it took for the particles to travel in both directions allows for precise determination of where the particles were upon detection. Therefore, the particles cannot be anywhere else after detection. Once a particle is detected, it loses its quantum wave characteristics. From all possible positions, it instantly assumes a position within a fraction of a second before it was captured by your flashlight. During the experiment, it's just like when the robot released a particle in the White Room. It moved everywhere until detected by the sensor. This irreversible process is called the collapse of the quantum wave. Similarly, you want to know at what speed it was moving at the point of detection. However, this is not so easy. In reality, you can never accurately answer that question. Remember, the shorter the wavelength, the more energy the corresponding light must possess. So, the more precise the position you obtain, the more powerful the light you need to use for your flashlight, making it harder to hit the particle. Thus, you have less information about its subsequent velocity. In our world, this might seem trivial, and statements like try to precisely determine the position of a moving object in the dark by shining something on it are straightforward. However, in the quantum world, it's not just a trivial uncertainty. It's a profound property of nature. It states that, ultimately, you cannot know both the position and velocity of a particle precisely. This rule is called Heisenberg's uncertainty principle, named after the German physicist Werner Heisenberg, who discovered it. He received a Nobel Prize in Physics in 1932. Heisenberg knew what he was talking about, but, like everyone since then, he didn't understand it fully. It lies beyond our intuition and contradicts common sense. The Heisenberg uncertainty principle immediately makes the quantum world fundamentally different from our everyday classical world. Right now, you know where your book is, relative to your body, and at what speed it's moving or not moving. Therefore, you know both the position and velocity with a high degree of accuracy. However, there's still some uncertainty regarding both parameters, but it's so negligible that it doesn't matter. In the microworld, at your tiny size, you wouldn't be able to hold the book, or even the flashlight, if you precisely knew where the mini copy of that book was. Uncertainty about its velocity would be immense, because you'd have to send a lot of particles to determine its position, and you'd never be able to see it again. Or conversely, if you knew its velocity precisely, you wouldn't have a clue about its position, no matter how many particles you send to find it. In the quantum world, position and velocity merge into a hazy concept. The same happens with the Casimir effect. As technologies get finer, engineers have to deal with this problem more often. Nevertheless, Heisenberg's uncertainty principle isn't a puzzle. It's a fact. In essence, it doesn't even represent uncertainty. It simply says our classical notions of position and velocity don't apply here. Nature operates differently, and we have predictive theories like quantum physics to explain it. The strange effects remain insignificant at our scales because we're continuously measuring the things around us. Why do all experiments show that the position of a particle suddenly forces the particle to be somewhere rather than everywhere? It's because particles exist as a possibility wave before the experiment. Afterward, they end up somewhere, and then they're everywhere again. Strangely, nothing within the laws of quantum physics allows for this collapse to happen. It's an experimental and theoretical mystery. Quantum physics dictates that in every case, when there's something, it can naturally turn into something else but cannot disappear. And since quantum physics allows multiple possibilities to coexist, these possibilities must persist even after calculations are made. However, they don't. All possibilities except one vanish. We don't see anything else around us. We live in a classical world where everything is based on quantum law, but nothing reminds us of the quantum world. This raises the question of how we can make quantum effects manifest on our human scale so that we can study and observe them, such as the collapse of the wave function. Is it possible, and if so, what would we expect to see? In 1935, just 2 years after being awarded the Nobel Prize for his work in quantum physics, Austrian physicist Erwin Schrödinger came up with an experiment to bring quantum effects into our scale. In this hypothetical experiment, he involved a cat and a box. Although it was just a thought experiment, scientists have continued to ponder it to this day. Is the cat alive or dead? You're about to redo Schrödinger's experiment, and I hope you don't have a strong affection for cute, purring, innocent playful kittens, because there's a good chance one might be harmed. With that disclaimer, let's proceed. For those of you unfamiliar with Schrödinger's cat, it's typically a furry, tail-wagging mammal that lives in the same reality scale as humans. Most people love cuddling with them. But not all of them are, well, usually green. To conduct Schrödinger's thought experiment, you've decided to select an adorable little black and white kitten and find a box that can be sealed so tightly that no one outside can learn anything about its contents except for the cat and the box. You'll also need a radioactive substance, one that is known to have a 50% chance of undergoing radioactive decay during the experiment. Radioactive materials are quite unpredictable. According to quantum laws, there's no way to know in advance whether they will decay and emit deadly radiation or not. It's a 50-50 chance. You've found such a substance. Now you need 3 more items: a radiation detector, a hammer, and a vial of deadly poison. You arrange them together in such a way that if the detector registers any radiation from the radioactive substance, the hammer will break the vial, releasing the poison. But here's the catch. You've placed all these items, the hammer, the radioactive substance, and the cat, inside the box and sealed it shut. Now you wait. And what's next? There's a 50% chance that the radioactive substance will decay and a 50% chance that it won't. Crazy experiment, right? Absolutely, and it should go without saying that you should never attempt this at home. So, what happens next? Is the cat alive, or is it dead? Quantum effects are at play here just as we wanted them to be, and the result is quite noticeable on a macroscopic scale. But if you don't open the box, there's no way to know whether radioactive decay occurred or not. So, there's no way to assert whether the vial is broken or intact, and consequently, whether the cat is dead or alive. Does this mean that we need to be cautious and use common sense when dealing with all things quantum, or not use it at all? To draw conclusions in the microworld, one must adhere to the laws of the quantum world, and in real life, you can expect that either the cat is alive or dead. But in the quantum world, something can both happen and not happen at the same time until observed. As mentioned earlier, most of the time, such superposition of possibilities goes unnoticed by us. For some unknown reason it doesn't occur or doesn't reach our scales. However, in this peculiar experiment, the settings are such that our eyes can see it simultaneously in both quantum possibilities, the decay and the non-decay. This is directly linked to either the dramatic death or the survival of the cat. So, what do the laws of the quantum world say? They state the following. The events of decay and non-decay are directly related to the fate of the cat. Until the box is opened, the cat cannot be considered either alive or dead. It exists in both states simultaneously. Before you open the box, the radioactive decay and non-decay events both happen and don't happen at the same time, just like the poison both spills and doesn't spill. And the cat is both dead and alive. Hearing this, you immediately open the box to check. The cat jumps out, completely unharmed, very cute, and not a dead one in sight. You scratch its head. All these superposition states subsequently collapse into a rather intricate trick rather than a real phenomenon. In other words, in the quantum world, strange things can happen, and common sense may not apply. To make sense of quantum phenomena in the microworld, you need to follow the laws of the quantum realm. In real life, you can expect either a live or dead cat in the box. But in the quantum world, it can be both until observed. This experiment demonstrates the weird and puzzling nature of quantum physics. Perhaps there was a misunderstanding. Was the cat truly both dead and alive for some time, or was it all a deception? Let's take a look. Opening the box makes you interact with the experiment, doesn't it? When you intervened and observed, nature had to make a choice. The choice to collapse had to occur, leaving the cat either alive or dead. But did the cat's fate freeze before you opened the box, or did it happen instantaneously? Returning to the initial question, does Leica Labs even exist? Schrödinger came up with his thought experiment in 1935, and for many years, no one could decipher its mystery. It wasn't until the French physicist Fraunhofer and the American physicist David Weinanda developed a real experiment capable of detecting those superpositions that were supposed to have already collapsed. Although they didn't use a cat, they used atoms and light and found that quantum superpositions are very real. Practically any quantum particle can exist in multiple mutually exclusive states simultaneously. Essentially, this is the main reason why engineers are trying to create quantum computers, harnessing the ability of quantum particles to exist in different states at once. In principle, quantum computers could achieve much greater processing power than what can be achieved with our classical computers, allowing for parallel computations. For their groundbreaking work, Arash and Weinand received the Nobel Prize in Physics in 2012. So, in some way, they proved that Schrödinger's cat was, at some point in the experiment, both alive and dead simultaneously. But what's the secret here? It's related to the disappearance of superpositions. That's what Arash and Weinand showed us. We have to accept it. However, when you opened the box, when the collapse occurred, and the live cat jumped out, what happened to the unobserved possibilities? And that's the secret. Many scientists have pondered the same question, and lately, a few proposed answers have gained popularity. Some believe that unobserved possibilities gradually dissipate, much like a drop of ink in a lake, with the lake representing the world in which we live. And that's the secret. Many scientists have pondered the same question, and lately, a few proposed answers have gained popularity. Some believe that unobserved possibilities gradually dissipate, much like a drop of ink in a lake, with the lake representing the world in which we live. It's as though pearls of unrealized possible realities scatter into a single prevailing reality, of which we are a part. Others think that our consciousness has something to do with it and that the mere act of conducting the experiment or even thinking about it freezes reality into one state, thus creating parallel realities. Here, we need the American theoretical physicist Hugh Everett III, born in 1930, who was said to be quite an eccentric character. A brilliant mind, he studied mathematics, chemistry, and physics, eventually completing his doctoral dissertation under the guidance of one of the most influential American physicists of all time, John Archibald Wheeler at Princeton University. However, Everett abandoned physics immediately after defending his dissertation, mainly because he apparently considered it too strange. Unsuccessful attempts to help his student be taken seriously by the scientific community probably played a role in this decision. At the age of 21, he transitioned to working on top-secret weapon development for the United States Armed Forces and eventually died due to excessive alcohol and cigarette consumption. His supernatural similarity to the fates of some famous poets or artists who quietly lived out their talents in their youth and were scorned by their peers played a role too. Nonetheless, Everett made an extraordinary statement in his 1956 paper, which later became a classic. He said that since quantum ideas work remarkably well on a microscopic scale, they should be taken seriously on the entire path to our scale. Thus, everything in our universe is created with quantum roots. Therefore, we should regard everything as a vast quantum wave of possibilities existing simultaneously. If you view it from this perspective, there is never a collapse. Every possibility exists. So, in a sense, a literal interpretation of quantum physics, as Everett put it, suggests that you are surrounded by parallel storylines. You hesitate between two elevators before entering one of them, and your other self in a branching parallel universe chooses the other elevator. In another universe, you bump into a shelf between them, and in yet another, you take the stairs. This way, all possibilities are realized. Essentially, according to Everett's theory, there's no collapse. Every possibility just exists. From this perspective, you'll never have to feel regret because every time something bad happens to you, there's another infinity of parallel realities where it didn't. And Virat is still alive and listening to this audiobook and some of them, liking that I don't see others, and writing this book himself in yet another. The cat in Schrödinger's cat, according to this interpretation, never makes a real choice by its nature. All possibilities just happen. You just don't know about it. It's not surprising that he turned away from physics. Undoubtedly, the theory of everything is captivating, but now it's taken seriously by some of the greatest physicists of our time, along with a multitude of mathematical models related to the origin of space-time. Of course, there's no experimental confirmation or denial of this statement yet, but it serves as a tempting reason why the reality we live in isn't a superposition of quantum possibilities, with unused ones embodied somewhere else. Now that you're accustomed to this idea, let's quickly recap what you've encountered here from the very beginning. You've traveled through different times, visited the micro-mega world, roamed cosmic realms, learned what the large-scale structure of the universe looks like and how it's governed by the theory of relativity. In the micro-world, you've seen that the laws of quantum nature differ from what we're accustomed to in everyday life. So far, you've traveled through known human knowledge, both theoretically and experimentally, and you've become acquainted with what constitutes the universe, regardless of scale, from the perspective of a scientist in the early 21st century. In this part, you've begun to touch briefly on the boundaries of this knowledge. You've seen that not only do general relativity and quantum field theory not readily communicate with each other, but quantum laws also seemingly don't govern our daily lives. This could lead some to believe in the existence of parallel worlds. In the 7th part, you'll explore even stranger things. However, let's continue to exercise your mind and leave the micro-world behind to return to Einstein. What about his theories? What mysteries can be found there, and do they exist? Are they more ubiquitous than we think, spoiling quantum field theory? The answer to the last two questions will be affirmative. Chapter 4, Dark Matter, Forget About Cats, Dogs, Parallel Universes, and Alternative Realities. Forget about cats, dogs, parallel universes, and alternative realities. Forget about the quantum world. Forget about mini-copies. Right now, you are in space, a sentient being. You've seen that the micro-world is filled with mysteries, and you intend to check if Einstein's theories work everywhere. They do have flaws, even without trying to turn them into a quantum theory. So, you're in space, leaving Earth behind and flying forward. You pass by the Moon and the Sun and reach neighboring stars. Up to this point, Einstein's theory of gravity works beautifully. Stars and planets move as they should. You head out of the Milky Way into intergalactic space, where you finally come to a stop. The Milky Way is now below you, and other galaxies are shining at a vast distance. There's a giant spiral of hundreds of billions of stars emitting light in the impenetrable darkness of the universe. So, what have you learned about the law of gravity? You know that, just like planets orbit the Sun, the speed of any star within a galaxy cannot be random. Stars that travel too fast will inevitably leave the safety of their galaxy. These solitary luminaries are doomed to eternal wandering through the vast expanses that separate individual galaxies from each other. If stars were moving too slowly, they would roll down the slope of space-time created by all the other stars. This slope would force them to move toward the galactic core, a central bulge filled with stars where they would ultimately be swallowed or destroyed by a supermassive black hole patiently awaiting its victims. Having insufficient speed to maintain a stable orbit, stars would either leave their galaxy or plunge into it, much like a marble rolling down or jumping out of a bowl. Remember how Newton's law of universal gravitation didn't work when gravity seemed too strong near the Sun? Einstein found these corrections, revolutionizing our view of space-time. Now, a century later, it's time to test Einstein's theories on a grander scale. Whole galaxies. You take out your stopwatch and start timing the movement of stars within the Milky Way. Simultaneously, you measure the speeds of 300 billion stars. This is why you started on the outskirts of the galaxy. From there, you begin. You clock a star for 10 seconds, and it has traveled 2,500 kilometers. Not bad. This corresponds to an average speed of around 900,000 kilometers per hour around the galaxy's center. This is a reasonable speed for stars within the Milky Way. In fact, any two stars at the same distance from the core of our galaxy have roughly the same speed. The slowest stars are far from the center, while the fastest ones, like the star S2 that you encountered earlier, are deep within. And if you're curious about how long it takes for these cosmic outliers to complete one orbit around the Milky Way, the answer is roughly 250 million Earth years, a long journey. The Big Bang happened about 61 galactic years ago, counted from today. If we start counting from today, in 20 more Milky Way revolutions, the Milky Way and the Andromeda Galaxy will get so close that they'll begin colliding. By the way, the Sun will explode a few galactic months later. Keep in mind that this is all within the context of cosmic time, which is vast and incomprehensible. You are experiencing a fraction of it, exploring the intricacies of our universe. So, this event doesn't seem as remote as it might appear. Everything is fine on that note, thank you. It seems like there are no issues here, except for one problem. To be frank, you're not the first person to check the dynamics of stars' rotation around the galaxy. Their speeds have been known for quite some time, starting from the 1930s when Dutch astronomer Jan Oort made measurements. But Ward went a step further. First, he estimated the amount of matter within the entire Milky Way and then checked if the observed speeds matched the expected ones for stars that don't fall into or escape the galaxy. They didn't match at all. Here, above the Milky Way, you can verify this yourself by adding up the mass of each star, along with the dust cloud and everything else visible within our galaxy. You'll come to the same puzzling conclusion: there's definitely not enough matter here to keep any star from being thrown out of the galaxy, considering its speed. Unlike the discrepancy in Mercury's orbit, which was tiny, there must be 5 times more matter than what you can see. Otherwise, all stars, including the Sun, should have been ejected. Perhaps you've missed something, and Ward also couldn't just overlook a few 100 million stars and the dust surrounding them. So, what's going on, and who is this Ward anyway? Can we trust him? He wasn't just an ordinary scientist. His incredible ideas helped humanity uncover much of what you saw during your journey through the solar system and the Milky Way in the first part of the book. He's credited with demonstrating that the Sun isn't at the center of our galaxy, a fact that may seem obvious now but wasn't until Ward proved it. He's also the man who proposed the existence of a vast repository of comets, billions and billions of them, beyond the gravitational influence of the red dwarf Proxima Centauri. Ward was an unconventional scientist, and following him, in 1932, he remarkably addressed the absurd discrepancy between the visible matter in our galaxy and the speeds of stars that don't fall into or escape the galaxy. Making a bold statement, he asserted that the Milky Way is filled with an unknown form of matter that had never been detected in any form, neither on Earth nor anywhere else, because it doesn't interact with light, rendering it impossible to observe with any type of telescope. He called it dark matter. As which's effects are manifest only indirectly through gravity, dark matter cannot be seen. But it warps space-time, just like ordinary matter, although it undoubtedly isn't made up of the same particles that compose all the matter we're familiar with. Otherwise, we would have seen it. This discovery might seem too vast and awe-inspiring to be true, but regardless of how good Ward was, nobody's perfect. He could have been wrong. To find out, you decide to look at other galaxies to examine their motion around each other in the same way Swiss astronomer Fritz Zwicky did, roughly a year after Ward's initial claim in 1933. If dark matter seemed real, gravitationally active not just inside the Milky Way but also outside and inside other galaxies, it wouldn't merely change the orbits of stars within galaxies. It would also affect the orbits of galaxies rotating around each other. So, you scrutinize the captivating cosmic dance of massive clusters of bright stars, and any lingering doubts vanish. Just like Zwicky, you're forced to admit that all galaxies rotate far too quickly around each other, hiding an immense amount of gravitationally attractive dark matter. Dark matter isn't normal matter, nor is it antimatter. It's something else entirely. Despite countless experiments since the 1930s and the bold hypothesis of Oort, we still have no clue what dark matter consists of. We know it exists. We know where it is. We even have maps of it within and around galaxies throughout the universe. We even have stringent constraints on what it can't be. But we have no slightest idea of what it is. And for every kilogram of ordinary matter composed of neutrons, protons, and electrons, dark matter weighing 5 kilograms, made of who knows what, dominates gravitationally. The unexpected gravitational mystery number 1 could imply that Einstein's theories don't work on these scales, just as Newton's theory failed near the Sun. But many independent studies have been conducted, and dark matter indeed seems to exist everywhere, around galaxies, including our own Milky Way, and throughout the universe. You can't see it. It seems that there is much more invisible matter in the universe than what is visible, leading us to dark energy. Billions of years have passed since the era of dark ages in our universe, and new galactic catastrophes have occurred. Entire galaxies collided and merged, the cruelty of space everywhere, and the galaxies you see are just the visible part. The dominating presence of dark matter, existing in overwhelming quantities of 5 to 1, cannot be seen. There is still so much of it that it must play, and continues to play, a role in the cosmic waltz you are observing. As you examine all these galaxies rotating around each other, the more dancers and figures you see, and the more inhabited worlds with skies vastly different from ours, you start to imagine. Suddenly, you find yourself wondering if some distant civilization has already found answers to our human questions. Then, you freeze in place, blinded by a very powerful source of light hitting your eyes. You peer into the night to determine where it appeared and notice it vanishing into the horizon. Suddenly, another beam of light, originating from an unimaginably distant place, strikes you. And another. You snap out of your reverie. You focus on the galaxies, contemplating where these light signals could originate. Not knowing why, your heart races as you watch the galaxies diverge, not following the path they should. We're not talking about their rotation around each other, but rather the expansion of the universe. How all galaxies are moving away. Like poppy seeds rising in dough. Considering what you've learned about this universal expansion, galaxies are moving wrongly. This is unexpected gravitational mystery number 2, and it implies much more hidden energy than dark matter. To understand, you need to know how distances are estimated in the universe. Imagine yourself on the shores of a tropical island, just before embarking on your journey into space. How could you tell which star in the night sky is closer and which is farther away? Clearly, brightness alone won't cut it. Stars come in various sizes, and their actual brightness can differ significantly. A bright star you see from Earth could be enormous and very distant, or it could be small but much closer. You need to employ a different technique, and historically, scientists have devised 3 distinct methods for gauging cosmic distances. The first one relates to any object, whether it's a planet or a star, relatively close to us. It's the simplest of all and uses common sense, no quantum physics here. Imagine you're looking at a tree through the side window of a speeding car on a highway. Trees growing close to the road whiz by quickly, while those farther away seem to move much more slowly. Mountain ranges on the horizon sometimes appear motionless. You can use them as a fixed background. In space, the same concept applies because the Earth orbits the Sun. Nearby objects seem to move noticeably against a backdrop of very distant stars, which appear almost stationary. By tracking how much an object's position relative to this background changes as Earth goes around the Sun, scientists can determine its distance in space. This method involves math that Euclid would have understood 2,200 years ago, and it works quite well for assessing nearby distances within the Milky Way. However, it falls short when gauging galactic distances. Galaxies are just too far away. When you're on Earth, spinning around the Sun, your view of space can change by 300 million kilometers from summer to winter. But this isn't enough to see their movements. Galaxies are still part of your static photo. To know where they are, you need method number 2, which involves a specific type of star called Cepheids. Cepheids are very bright stars whose brightness fluctuates between maximum and minimum levels with impressive regularity. Astoundingly, scientists have found a way to correlate this oscillating period with the total amount of light they emit. This is all they need to know to determine how far away they are. Just as the sound of a horn fades as you move away from its source, the same happens with light. Analyzing batches of light from distant Cepheids collected here on Earth yields their distance in the end. Fortunately, there are many Cepheids, but this method also has its limits. For measuring distances to very large galaxies and beyond, individual Cepheid stars can no longer be used because even the most powerful telescopes can't distinguish them from neighboring star groups. To explore the most distant corners of the universe, a third method is required. Perhaps you remember from the second part of the book the works of the American astronomer Edwin Hubble. In the 1920s, Hubble became the first person to observe distant galaxies receding and the expansion of the universe. Some of your friends kindly confirmed this fact by observing the night sky around Earth with telescopes purchased for $1 billion. In the 1920s, Hubble used the redshift of the light spectrum from distant galaxies to determine their speed and found that their tendency to move away from us is proportional to their distance. A galaxy twice as far from us moves away from us twice as fast. This law is now called Hubble's law. Method number 3 involves using Hubble's law from the opposite side. When Cepheids cannot be isolated from their surroundings by changes in the spectrum shift of radiation from distant galaxies, scientists can determine how far their light has traveled during the universe's expansion. This way, you can find out how far away a galaxy is right now. Hubble's law is quite simple and fits well with known facts. Space and time have become what they are today over billions of years. Since the intense energy release of the Big Bang, the expansion rate has slowed down over the subsequent 7 billion years. With this fairly logical setup, everything goes well, except that it doesn't match what you've just seen, powerful flashes of light that your eyes caught. The light flashes diverge from the law. The redshift doesn't fit the beautiful, coherent picture described above. Something is amiss, and the second mystery lingers. To understand what's going on, let's take a walk and look at what caused those extraordinary bursts of light that caught your eye. Starting from the Milky Way, you head towards a particularly beautiful and colorful spiral galaxy located 8 billion light-years away. You traverse vast, seemingly endless distances separating our cosmic family from this other speck of light. Approaching it, you enter it. As you pass by millions of stars through clouds of dust, equivalent to 1,000 solar systems combined, you suddenly stop again. Right in front of you, not just one, but two dazzling objects capture your attention. They are spinning very quickly around each other, somewhat asymmetrically. One of them is a gigantic red star, while the other is also a bright star but much smaller, about the size of Earth. They are both white-hot, though. Don't be misled. Despite the vast difference in size, the tiny star is the host here, not the red giant. The red giant is a massive star nearing the end of its life, and the small, white object is the remnant left from the core of a star that exploded hundreds of millions of years ago. During the star's death, its outer layers scattered in all directions, forming a long trail of bright, hot plasma. This trail spirals down towards its partner in this dance, creating a sparkling, twisting cosmic river that flows toward the surface of the white dwarf, where it gets compressed. Here, incredible energies are at play. Even space and time can feel their effects as waves, like ripples on the surface of a lake caused by two boats circling each other. Gravitational waves are generated by the dance of the red giant and the white dwarf, creating ripples that propagate through the very fabric of the universe, washing over nearby objects. As you watch, more and more matter from the giant star falls toward the surface of the white dwarf, and you can't help but feel that something extraordinary is about to happen. The white dwarf has indeed gained enough mass, reaching the critical threshold of about 1.4 times the mass of our Sun. At this point, the pressure in its core suddenly becomes high enough to trigger a new, incredibly violent chain reaction that leads to a rather remarkable demise. In an instant, it explodes, becoming a supernova, an explosion 5 billion times brighter than the Sun. It's a breathtaking cosmic swan song. Such events are called Type I supernovae, and they don't happen roughly once a year in any given galaxy. They are incredibly convenient for astronomers because they all look very similar, even identical. They always occur when a white dwarf reaches 1.4 times the mass of the Sun after siphoning energy from another star, and thus, they always shine with the same light, equivalent to 5 billion suns compressed into one small spot. Not much larger than our Earth, but much brighter. They are perfect candles that allow us to explore the farthest corners of our universe and test Hubble's expansion law. Type I supernovae are so much brighter than everything else that, unlike Cepheids observed with man-made telescopes, they can be identified in distant galaxies. Knowing their true brightness, just like with Cepheids, scientists can determine how far away they are and at what speed they are moving away from us. In 1998, two independent groups of scientists studying such distant supernovae published their results. One group was led by American astrophysicist Saul Perlmutter, and the other by American astrophysicists Brian Schmidt and Adam Rees. Both teams discovered that around 5 billion years ago, after more than 8 billion years of regular behavior, the expansion of the universe began to accelerate. The scientific community was shocked, just as you might be. Not only was this conclusion unexpected, but it was radically opposite to the only expected result. On a large scale, everything is governed by Einstein's general theory of relativity, a theory of gravity. Like Newton's law of universal gravitation, both of these theories only allow for attractive interactions between objects. Therefore, to prevent the universe from collapsing under its own gravity, some form of matter or energy must ultimately slow down any expansion rather than accelerate it. However, the observations of Perlmutter, Riess, and Schmidt indicated otherwise. The only way out of this contradiction was to find something entirely new to explain this apparent acceleration. This new something had to fill the entire universe and possess the unique property of acting as an anti-gravitational force, pushing matter and energy apart instead of pulling them together. For some unknown reason, this new force went unnoticed until about 100 years ago. Einstein himself, as you might remember from the second part, didn't like the idea of a changing, evolving universe. He preferred to think that time and space were fixed and unchanging, something he could feel from his own experiences. Unfortunately, his own general theory of relativity, in its simplest form, suggested otherwise. It allowed for space-time to change and had to accommodate something new to explain this change, which he called his biggest blunder. Today, it seems that his blunder was not calling it a blunder. In fact, the new term added to Einstein's equations imply that energy would fill the universe and would have the power to change the universe's dynamics. Einstein imagined that the cosmological constant, as he called it, could hold the universe steady, obedient to his philosophical beliefs. A steady Einstein could sleep at night. However, about 10 years later, Hubble's work transformed the expanding universe into an established fact, and a static universe was no more. Thus, Einstein erased his cosmological constant and labeled it as his biggest blunder. Ironically, a century later, it appears that what he erased on paper could have become a tool for theorists to explain the greatest unsolved mystery of humankind: dark energy, which drives the acceleration of the universe. Cosmological constants can make the universe exactly the opposite of static, subject to rapid and accelerating expansion. It can solve the dark energy puzzle, and its only problem then is figuring out its own source. We will come back to this in part 7, but for now, I would like everyone to consider such mistakes as Einstein's. Whatever dark energy turns out to be, the idea has already changed our view of cosmology. Whatever dark energy turns out to be, the idea has already changed our view of cosmology. Before the discovery of Perlmutter, Riess, and Schmidt, there were two possible future scenarios for the universe, depending on its overall contents. In the first case, if there was too much matter, the expansion was doomed to eventually reverse, and gravity would overpower everything, resulting in a big crunch, like a reverse Big Bang. In the second scenario, if there wasn't enough matter or energy to halt the expansion, the presence of dark energy would ensure that the universe continued to expand at an accelerating rate, heading towards a big freeze. Both scenarios seemed rather grim. However, as you will see in the next and final part, such a freeze may not be the end. I'll repeat it once again, it's also possible that Einstein's theories are simply not applicable at such vast scales. In that case, we cannot use his equations to conclude the existence of dark energy, much like how Newton's theories, tested near large stars, led to incorrect predictions about orbits. Einstein's equations could, at some point, depart from reality. However, as of today, it's more likely that dark energy is real and even has a quantum nature, a highly exciting prospect for scientists who seek to connect the microscopic and macroscopic worlds. In any case, whether dark matter and dark energy are real or not, Newton's law of universal gravitation has helped us discover new planets around the Sun. And Einstein's theory of gravity has led us to mysteries much more profound. So profound that they may contain clues or keys to opening the door to unknown realms of our large-scale reality. With necessary humility, such discoveries make a strong impression. And now it's time to understand why Einstein's theory of relativity cannot be the theory of everything and why it predicts its own demise. Chapter 6, Singularities. Remember quantum infinities? Remember the catastrophic consequences for spacetime when an infinite number of particles pop in and out everywhere, all the time, in the vacuum of quantum field theory? To study them, scientists either had to eliminate gravity, as if it didn't exist, or ignore the ones in the microworld. Everything worked just fine until gravity had to be quantumized. Now, let's leave all those quanta aside for a moment and focus on gravity itself. Could it be that the familiar matter, classical matter we interact with every day, has the same effect on the fabric of spacetime as an infinite number of particles on rubber sheeting? The answer is a definite yes, and this time, we'll even see it in the sky. Here's a well-used analogy. Imagine several very heavy marble balls placed on a thin rubber sheet. Due to the weight of the marbles, the sheet will curve and bend around them, creating a well into which the rubber bends even further. At some point, either because no more balls are rolling down or because the remaining balls are too far away, the process will stop, and there's nothing strange about that. But if the rubber sheet is soft, like gum, and not strong enough to hold up a heap of marble balls in equilibrium with its tension, it can keep bending more and more, even if no more balls fall onto it. Until a point is reached where nothing can stop the increasing curvature, even though nothing else is falling in. While no material is strong enough to withstand any weight, here comes the idea of a density threshold. If you put too much weight on a too fragile surface, it will inexorably start curving more and more, even if nothing else falls onto it. As the curvature continues, what started as a bend gradually becomes a pinch, as density increases inside, creating a runaway process inevitably leading to the collapse of spacetime. Collapses, exacerbated by infinite infinities that general relativity can't handle. Such infinities are called singularities. They are not the same as the quantum infinities you introduced earlier. As the light source, they become small bright strips covering the outer edge of the dark disk, and then they disappear, as if swallowed by the dark void before reappearing on the other side, where the sequence of distortions is reproduced in reverse until they again become like distant sparkling points of light. It seems like light is bending around this hole, seemingly expanding from the inside like a dark shaft, while its edges act as curved lenses. Accompanied by the robot, you continue to spiral downward. You're still quite far from what will turn out to be a black hole, but you already feel the inevitability, and suddenly you want to escape before it's too late. Before it shows you what lies beyond. Look over your left shoulder, the robot says after a minute of silence. Turn around. Huge boulders head straight for the black hole. This rotating asteroid, the size of a mountain, races with astonishing speed, about 100 kilometers away from you. You focus your sight on the dark silvery surface of the asteroid, the only object moving toward the black disk of the black hole. The true size of the asteroid shrinks as it moves away, now the size of a peach at arm's length, and then the size of a small, distorted walnut. Suddenly, as your spiraling descent carries you to the other side of the black hole, two images of the asteroid appear at once, one to the left and one to the right of you. The distortion of space-time around the dark spot seems to give light the ability to reach your eyes by multiple paths. The asteroid will soon disappear, the robot says, almost with regret. Disappear? You ask, becoming increasingly worried. What do you mean by disappear? Through what? Through the horizon? Through what? Through the horizon, the robot clarifies. The point of no return. Will you see it or not? No human or machine has ever been this close to a black hole, let alone inside one. There's a theory about what should happen down there, but it could be wrong. Passing through the horizon, we leave the boundaries of the known. Maybe we shouldn't get too close, you suggest. Or maybe we should, the robot replies. This is an exploration. We'll have to accept some possible risks. Or should we look for the horizon everywhere, pointing our tube left and right? The robot alternately points to two opposite places near the edge of the black hole, in the direction of the two images of the asteroid between them. Now, shifting your gaze from one image to the other, you wait for both to continue falling and disappearing over the horizon in the hole. But by the time you complete another revolution, the small, walnut-sized silvery brown asteroid is still floating above the dark void, strangely unaltered. 4 times when you were directly above it, it hadn't fallen. In fact, it seems like it's not going to move or rotate anymore. It's not falling. It's not falling, you shout with relief. So, maybe today won't be the day I get torn apart in a black hole? Falling in, the robot corrects you. It's not there anymore. It's just its image, the distortion of space and time at work. Our time, yours and mine, doesn't flow the same way with the asteroid. It's already beyond the horizon. While you're still trying to grasp this, 2 more images of the asteroid, and the diamond-like object appear, passing by you as surrealistic distortions in the darkness, becoming increasingly distorted. And the same happens to the rest of what you can see. Why did you want me to see that? You ask the robot. As the empty gift grows, devouring things, black holes are far from empty, the robot solemnly declares. In fact, they are the opposite of what happens when too much matter and energy are confined to too small a space. To create them requires colossal energy. As far as we know, only the largest, brightest stars emit enough energy to make a whole one. While we've encountered remnants of stars, like white dwarfs during our journey, they are not nearly as extreme as black holes. All these remnants of stars are impressive, but black holes go beyond all of them. And since we're here, as you continue to spiral down a few more rounds around the black hole that you inevitably approach, let me mention another reason why they are so frightening and mysterious. If you found yourself on any object in the universe, be it an asteroid, planet, or star, you could send a light signal from there to determine your position. However, the denser the object you find yourself on, the more energy your signal would need to ascend the slope created around that object in space-time. It's similar to a marble. The deeper it is, the faster you need to roll the marble at the bottom to spiral all the way up and out, sitting on a planet, star, or white dwarf. You must sequentially send more and more energy to send the signal into space to avoid its gravitational attraction and falling back into a black hole. What's worse, they contain so much matter and energy that they create such a steep space-time slope that anything getting too close to them is doomed to fall in. According to the general theory of relativity, nothing in our universe has enough power to avoid gravitational capture by a black hole, not even light. The point of no return, beyond which nothing can escape, is the event horizon of a black hole. It lies somewhere there, where apparently frozen images of asteroids and diamonds have crossed. If you look at them from beyond its boundaries, darkness continues to grow in front of you, like a gaping mouth ready to swallow your real essence. Distant stars everywhere now look completely different. You even have the confusing feeling that what you see in front of you is actually behind you. When you turn your head, you realize that it's not just a feeling. It's a real fact. The light emitted by the star shining behind you, traveling at its usual speed, overtakes you and rushes down the slope created by the black hole. All the rays emanating from the monster's left side now reappear on its right. It's like a 180-degree turn on a roller coaster, and then these rays turn toward you, dazzling you. So, looking ahead, you see what's behind you. As you continue to spiral down, everything becomes even more tangled. The images of asteroids and diamonds are now in motion again as you get closer to them. Your time converges with theirs, and then they suddenly disappear completely. You just saw them cross the horizon which they incredibly covered several hours ago in their own time. The robot flying next to you turns, and its tube now points towards space. You also slowly turn, fearing what you might find there. What you see lies beyond imagination. All the stars that were everywhere, frozen a moment ago, are now moving. The absence of their immobility, usually imperceptible, and even segments of the length of a human life now become evident to you. Now, for you, they are obviously all approaching and, in some cases, moving so fast that they even leave traces on your retina. The fading light curves on your universe map, just like when you traveled through the universe, accelerating closer to the speed of light. You observed the lives of a cosmonaut, his children, and their children flying in the past, and their paths accelerated compared to yours. This time, it's all because of gravity, due to the curvature of space-time caused by the presence of a black hole. Here, around the black hole, your time flows slower than anywhere else. You see the unfolding future of the universe, and again, this is what space and time combined in space-time imply. We've already crossed the horizon suddenly. You ask anxiously if we have to fall inside. The robot turns again to look at you, and you are amazed to realize that its tube has widened. In fact, it looks like it was meant for throwing, not particles but bowling balls. We haven't crossed it yet, it replies, but you can hear a hint of amusement in the robot's voice. However, before you can react, it fires a heavy projectile straight into your chest. You're unable to avoid the impact, and you have no choice but to catch the flying object instantly. Its speed propels you downward toward the gaping darkness. You scream desperately, trying to grab onto something to halt your fall, but there's nothing around to hold onto. You're falling. The robot recedes, and one of your seconds equals one of its minutes, then an hour, then a day, and now a year, while the robot continues to move away for millions of years. Stars pass by you, new stars are born, and you see all of this. You've crossed the horizon of a black hole, shocked. You gaze into the future of the universe, utterly consumed by fear. With no strength to focus, you fall into a fetal position, gazing upwards at the unfolding life of the universe, while you yourself disappear into the abyss of unknown non-existence. At its core lies a singularity, and now you lower your gaze to look into it, into the mysterious heart of the black hole, where the opposite of non-existence itself, matter creating all this nonsense, must reside. Somewhat to your astonishment, you see nothing more. Not even your body, no feet, no nose, not even your own hands. Light can fall on you from above when coming from outside, but from here, nothing can rise from the inside in any direction, regardless of its proximity. Light lacks sufficient energy for that. You've crossed the event horizon of a black hole and are now condemned to fall eternally toward the surfaces of many collapsed stellar remnants that have merged during this infinite descent. Space-time is stretched too much for Einstein's general theory of relativity, with unknown consequences. In reality, if you were really there, you'd be dead, because even light can't make the tiny journey from your feet to your eyes. There's no way blood could climb up the slope of space-time you're sliding down to reach your brain. But since we have much more to see, we assume you're still alive. Unwilling to gaze into the abyss, you decide to look up again at the universe and how its images flow down toward you through the now pouring over event horizon. However, any movement implying a part of your body moving upward and outward is prohibited. It would require energy that not even light possesses. Any upward movement is forbidden, and as you start to wonder if there's anything worse than this, tidal forces begin to torment your body. The gravitational pull of the invisible presence of the black hole starts to tug your legs downward harder than your arms and head. The black hole's gravity elongates your body. You're about to end your life stretched out like spaghetti. Even if the cunning robot equipped you with the most powerful rocket engines ever invented, it would change nothing. Regardless of the engine's power, as soon as you try to move upward toward the black hole's horizon, you'd feel yourself being stretched out on the slippery stretched fabric of space-time. It's like a continuously operating treadmill with a speed always surpassing yours, dragging you downward. According to Penrose and Hawking, you are now subjected to the gull or stretching of space-time somewhere down there, hidden beneath the horizon. No light rays are allowed to penetrate the singularity's heart and return. Such places seem destined to forever remain shrouded in mystery. According to the general theory of relativity, neither you nor any belonging to you will ever escape from there. Sad thoughts, especially now that you've been torn apart, turned into a long thread of those particles composing your body. But don't trust the general theory of relativity down there, because we must remember that it's not a quantum field theory. Hope immediately returns as you transform into a mini copy, waiting for the process to start anew. At first, nothing happens, but then, surprisingly, you see that all the elementary particles making up you disappear or make a quantum leap, to be more precise. Essentially, they perform a quantum jump, and now they're outside the black hole where, fortunately, they assemble into a mini copy of you. You're met by the robot again. At this moment, you're very tempted to pounce on it and try to rip the metal tube from its body, seeking revenge for the shot that carried you beyond the black hole's horizon. But before you can do anything, you hear the robot's metallic voice say, "I've been waiting for you for about 10 billion years. I'm glad you recognize me." Suddenly, your resolve to harm it vanishes. There are more important things to contemplate, not the least of which is what you've just experienced, involving gravitational and quantum fields interacting with each other all around. Stars are moving again almost imperceptibly slowly. Indeed, it's been about 10 billion years since you were ejected beyond the black hole's horizon. You look at the dark spot of space from which you miraculously escaped. At first glance, it seems to have changed little, but now that you know what to look for, it's as if another curtain has been drawn aside. You genuinely see the particles escaping from the black hole. They're moving away from it, and you get the feeling that the dark monster is evaporating. Maybe this is happening all the time, you realize, but you just didn't notice. But how can this be? As Richard Feynman once said, anyone who claims to understand the phenomenon must be able to provide many different reasons for it to happen that way. While you and the robot observe the torrent of particles escaping into space, I'll give you 4 reasons why particles flow through black holes. They're all related to the process you've already encountered. The first one is the simplest. As you know, quantum particles can borrow energy from their fields, even when they are beyond a black hole's event horizon. With this borrowed energy, they can briefly move faster than the speed of light, long enough to make a quantum leap from the black hole's point of no return. This is what you did when you became a mini-copy. It's a quantum process. All the ways to understand what happened to you are inherently quantum. So they all come with the usual health warning, because, like much of what you've seen in the quantum world, they may seem absurd. The second reason, not excluding exceptions, can be said that all the failed particles simultaneously did and did not do through the horizon of a black hole. Out of all possible paths, the considered one as a wave may choose to fall into the hole, and in most cases, it will miss because beyond the black hole, there is much more space than inside it. Surprisingly, but this carefully developed idea makes the black hole evaporate, just like the first reason mentioned above. The third reason is as follows. Due to the vacuum force separating beyond the black hole's horizon, which is different from the vacuum outside, a certain vacuum force effect known as the Casimir effect pushes the horizon inward. As a result, the black hole contracts and evaporates. Again, miraculously, This yields the same result as the previous one. The fourth and final reason I will mention here is that the birth of particle-antiparticle pairs occurs near the horizon of black holes, and these particles fall inside more often than they fall outside. However, ultimately, they annihilate each other, causing both of them to disappear, leaving only the particles created together with the original particle. Annihilating inside again yields the same result. All these quantum effects were observed before, but here they are applied in close proximity to a black hole, and they all lead to the same conclusion: black holes evaporate. So, when you now look at the glow of a black hole, you understand that this cosmic monster, once a black hole, has been devouring entire stars for billions of years. It's no longer black but gray, and it's shrinking even more astonishingly. What's even more amazing is that the more particles it emits, the hotter it becomes. And the hotter it gets, the more particles it ejects. It's a closed loop, leading to the host's death. The black hole, no matter how incredible it may seem, shrinks, emitting energy, space-time storing its energy, as it absorbs entire worlds. Now, this energy returns to cosmic space, particle by particle, at every moment, just like radioactive decay. The black holes that existed around us are bursting, giving particles a second chance. All the nature's quantum fields, excited by what is nothing other than the most powerful gravitational object known in the universe right now, are being utilized up to an unexpected golden bottom to fill themselves with energy. As the black hole becomes hotter, its fundamental particles, dormant until now, awaken and emerge. You can see how it happens. And the smaller the black hole becomes, the more excited the fields. And the more energetically it ejects gravitational energy particles once again transform into matter and light. While the whole process unfolds before your eyes, you realize that it is full of contradictions to the laws of the Earth. Hot water in a cup on planet Earth does not heat up and evaporate. Usually, it cools down. If it were otherwise, a forgotten hot coffee on the table would lead to a catastrophe, and the evening news would be full of stories like another cup of coffee ignited a table, leading to the building's fire. Don't forget to always cool your hot beverages. Black holes are clearly different from coffee cups. The more they evaporate, the more they contract, and the hotter they become. No one knows what happens at the end of this process. Do black holes disappear with a final explosion? Or do they leave behind strange tiny remnants with special properties? To find the answer, we need to understand the laws that govern the singularity hidden deep inside. Scientists have been searching for them since 1975, the year when Stephen Hawking discovered on paper that black holes evaporate. At first, he didn't believe his own calculations. The light seemed to be coming from a place where there was supposed to be no light at all. So he repeated his calculations, only to confirm that light particles had indeed found a way out of black holes. He published his discovery in journals, and instantly, he became known worldwide, outside scientific circles. Quantum effects have caused black holes to evaporate, preventing anything from getting stuck inside them forever. They emerge in an unusual way, possessing the ability to evaporate. Black holes behave as if they have a temperature, now known as the Hawking temperature. Observing the remnants of energy emerging from black holes, you understand that something you're looking at tells you that the micro-world and the mega-world can communicate if necessary. They have to do it in a unique way, radiating from black holes. So far, this radiation is the only evidence that our theories can reflect nature in this regard. It's a specific hint that quantum gravity theory might still be possible. Any serious contender for such a theory will have to calculate the Hawking temperature of black hole evaporation all the way to the black hole's death. Black holes can die, he said in a loud voice. It's hard to believe, like everything else in this universe, the robot added. But in the late 1970s, Stephen Hawking's discovery also led to a rather strange and quite disturbing statement. Having his formula for the Hawking temperature in hand, Hawking attempted to extract information about what constitutes a black hole by throwing various objects into a fully formed black hole. He wanted to see how each one transformed and emitted subsequent radiation. Surprisingly, there was no difference in the emitted radiation regardless of what was thrown into the black hole. The emitted radiation did not convey any information about what had fallen in. Apart from their mass, nothing else could be discerned. It seemed that black holes completely rid themselves of the characteristics of what they had absorbed, except for their mass. Whether it was people, books, asteroids, or diamonds, if they had the same initial mass, they would subsequently evaporate in exactly the same way. So, according to Hawking, for black holes, people, books, and rocks all tasted the same. For us, this means that only our mass matters to black holes, which might affect the self-esteem of some. However, this posed a philosophical catastrophe. Prior to Hawking's work, it was assumed that black holes absorbed everything that crossed their event horizon and grew, and this didn't seem to be a problem. Everything that fell inside was not lost. It was simply stored beyond the horizon. Retrieving it was difficult, if not impossible, but who knew if it could be brought back? With the stunning revelation of black hole evaporation, things began disappearing from reality. The fact that Hawking's radiation was independent of what precisely fell into the black hole meant that these dark monsters became memory holes for our universe. Information stored within black holes, along with the black holes themselves, were no longer accessible. The information had vanished forever. Science and the foundations of theories, everything, were lost. The theory that explained everything in one formula, and the first result achieved from such an attempt, dealt a blow to science as a means of understanding. Where the universe came from became a problem again. This problem was compounded by the black hole information paradox. Today, physicists are more familiar with the rough approximations that Hawking used to obtain results. But even 40 years after his discovery, when Hawking asked me to work on this problem with him, it remained shrouded in mystery. Now, hints have emerged that a solution may be found by applying what is known about the quantum world to black holes themselves. It turns out that black holes may or may not have existed, and where these contemplations led scientists, you will learn in the next concluding part of the book. But for now, in an unknown number of billions of years in the future, you suddenly remember the robot's suspicious happiness about your return from the black hole. Did it surprise you back then? Why was he so delighted that you remembered him? You thought it was genuine, didn't you? But perhaps it wasn't. And now you know why. The robot wasn't sure if you remembered anything at all. He didn't know if the black hole erased your body and mind. And when you tried to tear him apart for pushing you, he realized that you had remembered. The information in your case was not lost, even if you have no recollection of how you managed to return through the black hole. You remember becoming a collection of fundamental particles and then finding yourself outside. Something akin to a quantum leap occurred. Understanding how this could have happened precisely is what the field of quantum gravity theory aims to achieve. As that is what you will explore in the near future, let me emphasize the fact that this part of the book has taken you into the realm of pure theory. Dark matter has never been created in a laboratory, just as dark energy has not. The same is true for black holes. Their evaporation has not been detected by any experiment, directly or indirectly. Otherwise, Hawking would have received a Nobel Prize. The evaporation of black holes is a particularly difficult road. To illustrate, let's take the Sun. To turn it into a black hole, you would need to compress it to a sphere about 6 kilometers in diameter. This is approximately 2/3 the diameter of Greater London. Most black holes in the universe are formed when massive stars die, so they must be larger than the Sun, which is not a giant star. Now, let's assume that one of these solar mass black holes has swallowed everything nearby and now quietly exists somewhere far away from everything else. Its temperature, the Hawking temperature, should be approximately 1/10 of a millionth of a degree above absolute zero. Absolute zero is about -273.15 degrees Celsius, so 1/10 of a millionth of a degree is not much. It's challenging to measure. However, this is not the main problem. The main problem is that the Hawking temperature is much lower than the cosmic microwave background radiation temperature, which is 2.7 degrees Celsius above absolute zero. This radiation permeates the entire universe. As a result, solar mass black holes are not currently considered to be evaporating. To be honest, no one has ever seen them in this state. They exist and have always been masked by the residual relic radiation from the Big Bang era. And the larger the black hole, the lower its Hawking temperature. So, supermassive black holes sitting at the centers of most galaxies have even colder Hawking temperatures than solar mass black holes. Not to mention that they are surrounded by extremely hot accretion disks of falling matter. Therefore, the potential Nobel Prize-winning phenomenon Hawking described may exist in the micro-world, where tiny black holes should be very hot. Unfortunately, there are still problems. Scientists are fairly confident that they have observed giant black holes, but have never seen a tiny one. Let's assume they exist. Can we practically extract anything from them to find out? Allow me to digress briefly into a topic that sheds light on what I previously referred to as the Planck wall. In the early 20th century, one of the most impressive scientists of all time, Max Planck, a German like Einstein, established what we now call quantum physics. He received the Nobel Prize in Physics in 1918 for his own discoveries. Planck realized that there is a scale beyond which quantum effects cannot be ignored. Take a large object, and everything is fine. You can apply Newtonian understanding of nature to it, and regardless of what is expected of it, it corresponds to the reality we are accustomed to in our daily lives. But compress that object to microscopic sizes, and Newtonian physics starts to fall apart. Planck introduced a way to describe the world at a familiar human scale, which aligns with our common sense. Einstein's view predominates for the macro world, and Planck's quantum world reigns for the micro world. These are the natural constants that tell us where they begin to break down. One of these constants is called the Planck constant, which is on equal footing with two other universal constants, the speed of light and the gravitational constant, which tells us how two masses attract each other. Planck played around with these constants and created three things. One of them was the Planck mass, which turned out to be about 20 micrograms, 1/1,000,000th of a gram. This is called the Planck mass, and it strangely isn't much. But if you managed to squeeze the tiniest volume of space-time into it, it would evaporate in 10 seconds, Planck time. Now, let's assume we could measure such tiny, rapidly occurring events. Then we would need to create a Planck mass black hole for study. However, with our current technology, to create such a black hole through the collision of high-speed particles, the accelerator would need to be the size of our galaxy. Obviously, this is far beyond our capabilities, and I doubt anyone is willing to undertake such a project, except for Hawking for understandable reasons. However, consolation may come from outer space, where these tiny black holes could be detected if they emit their last energy. This would only happen if an, as yet unknown, phenomenon decides to tell us where and what to look for. Someone could get extremely lucky and detect it immediately. Still, no one doubts the existence of Hawking radiation, which means that somewhere in the micro-world, a new quantum reality exists, encompassing space and time within itself. It is due to this that, as you will see shortly, in the minds of some of the brightest living scientists, the most unusual picture of our universe has emerged. Part 7, Beyond the Known, Chapter 1. Let's go back to the beginning. As you've already seen, the visible universe is not infinite, and the Earth, along with you, is at its center. This is practically a fact, and the key word here is visible. The visible light reaching you from one direction brings the past that is as remote as from any other direction, making your cosmic surroundings appear spherical. This doesn't mean the entire universe has a spherical shape. It simply means that only the part visible to you has this property. The oldest light reaching you today left the surface of the last scattering wall at the end of the observable universe about 13.8 billion years ago, when the universe had cooled down enough to become transparent. It is believed that at this last scattering, the universe was about 380,000 years old and had a temperature of 3,000 degrees Celsius. After this moment, it expanded and cooled down. But make no mistake, it was much smaller before this last scattering. So, the visible universe can be thought of as a sphere with the Earth at its center, composed of all the past that reaches us today. The outer edge of this cosmic archipelago consists of layers from different epochs of the universe's history. The outermost edge of our observable past is also a part of the present moment, the history of our universe when light and matter were no longer confined. You were there. You saw this wall. You didn't even cross it, but there is something special about it, something very strange that you may not have noticed then. Do you remember what your friends with billion-dollar telescopes discovered when they gazed at the night sky? They found that the radiation filling the universe was almost the same as in other parts of the deep night sky. But where did it originate? It's called the cosmic microwave background radiation, and it's a relic of the Big Bang theory. It was undeniable evidence required to prove that our universe was much hotter in the past. But, my friends, neither you nor your friends paid attention to the fact that this radiation was too homogeneous to match what is expected from the expansion of our universe. As you can see now, this extraordinary homogeneity is one of the reasons why scientists came up with the idea of the cosmic inflation epoch, which occurred earlier and triggered the Big Bang. About 380,000 years before the universe became transparent, you are there too. And this event opens up the possibility of one of infinitely many Big Bangs. Ask your neighbors to turn off the lights at night and sit in a chair to look at the sky. Your eyes will be filled with the light of deep space, the cosmic microwave background radiation. Despite being too weak for you to see without the right equipment, if you look long enough and with the right instruments, you'll register the radiation. Eventually, you'll get a fairly homogeneous picture, showing a temperature of minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, just above absolute zero. Now, take your chair and move to the exact opposite place on Earth, the antipod. If you started from the UK, you're now in the middle of the Pacific Ocean, surrounded by darkness. You're on a raft in a chair, looking at the sky, collecting light that has traveled across the universe for 13.8 billion years. Still at minus 273.15 degrees Celsius, it's the same cosmic microwave background radiation, but there is absolutely no reason for it to be the same everywhere. In fact, such a possibility should be ruled out. The relic radiation that reached you in the UK came from one end of the observable universe, while the one you're capturing in the middle of the Pacific Ocean comes from the opposite direction. The sources of this light are so far apart, 2 times 13.8 billion light-years away, that unless something strange happened at some point, there's no way for them to have been in contact throughout the entire history of the universe. So, they shouldn't have the same temperature. To understand how strange it is for them to eventually have the same temperature, think of it this way: take a hot cup of coffee and bring it into your living room. Unless you live in an oven, the temperature in your living room should be lower than that of the coffee. But if you wait long enough, the coffee cup and the room will eventually reach the same temperature. Now, take that hot cup of coffee, put it in the refrigerator, and close the door. Again, after some time, a new thermal equilibrium will be reached, and this time it will be even colder than the previous equilibrium. All of this sounds normal. Nothing strange, right? Now, Pour yourself another cup of hot coffee and place it in your living room. It is highly unlikely that it will eventually have the same temperature as the inside of the freezer in Japan. Two objects or places that have never been and will never be in any contact, and aware of each other's existence, have no basis for eventually having the same temperature. This fair assumption must also apply to cosmic space for the two opposite ends of the night sky, separated by 13.8 billion years, to share the same temperature of -273.15 degrees Celsius. They should have somehow contacted at some point in the past, but it doesn't seem possible, given the age of the universe and the rate of its expansion. They are too far apart to ever interact in any way, unless something very, very strange happened. For example, something that could move faster than light. Unfortunately, for signals, which means anything that can carry information regardless of its form, from one place to another, it's not possible. We're not talking about quantum processes here, so signals, as you probably know, cannot travel faster than the speed of light. This is strictly forbidden. However, the temperature of the cosmic microwave background radiation is too uniform everywhere to be a coincidence. How can this be? It might turn out that space-time itself, or the universe in other words, grew faster than the speed of light at some point in the past, and this is what you witnessed. Traveling back in time beyond the Big Bang, when you entered the so-called inflation era. During this epoch, the universe was filled with an inflaton field in its modern form. The inflationary model of the early universe was first proposed in the 1980s by American theoretical physicist Alan Guth, Russian astrophysicist Alexei Starobinsky, and American theoretical physicist Andrei Linde. The Standard Model suggests that long before the emergence of matter, light, and everything we know beyond the visible universe and before the Big Bang, there existed a field that filled the universe with a repulsive anti-gravitational force. This field was so extraordinarily powerful that it caused a period of accelerated expansion, which separated various regions of the early universe from each other at speeds much greater than the speed of light. This allowed places that appear too distant from each other today to have actually been in contact in the past. This is why the concept of the inflaton field emerged. But can we really detect any of its fundamental particles if the field is real? Most of its particles should have disappeared long ago, contributing to the hot Big Bang. However, it couldn't completely vanish. The inflaton field, or the inflaton itself, must still exist to some extent, surviving in one of its lowest energy states, the vacuum. Because of the lack of sufficient energy, it's highly unlikely to ever become excited enough to produce light and reveal its particles to us. The inflaton field, or the inflaton particles, are not well understood yet. However, many scientists believe that some scenarios of the inflationary model, with its inflaton field, should closely resemble what actually happened. I personally find this idea quite appealing. So, let's take it seriously and explore what the history of the universe containing such a field and inflation could look like. The inflaton field did an excellent job of separating different parts of our visible universe so rapidly that they never came into contact. This separation continued until the Big Bang, when everything with its fields and particles emerged from a colossal amount of energy released at once. Then, the universe began to expand normally, and the inflation didn't play a role anymore. However, around 8 billion years after the Big Bang, after stable growth of our universe's matter, which gave rise to the inflaton and other fields, it turned out to be enough for its vacuum to wake up again, with dramatic consequences. Its anti-gravitational force led to the accelerated expansion of the universe. The experimental discovery of this acceleration in 1998 by Perlmutter, Schmidt, and Rees led to the Nobel Prize in Physics in 2011. Of course, how the inflaton field affects the behavior of the universe today is nothing compared to how it scattered everything into different directions before the Big Bang during the inflation era. Nevertheless, it might be responsible for the future that awaits our reality. Antipodes and parts of the universe, as seen from Earth, are now too far apart to ever be in contact again. However, it did happen before the Big Bang. So, these opposite parts of the night sky have every reason to behave similarly. Could this be the appearance of a new field, the inflaton field, simply a clever solution to explain why diametrically opposite points in the night sky have the same temperature? Or did inflation actually exist, and is it possible to verify? Amazingly, it might be possible. Chapter 2, The Multitude of Big Bangs. Some time ago, you conducted an experiment with a cat, Schrödinger's cat, with the aim of finding a method to express a strange microscopic quantum behavior in macroscopically observable reality. We're doing just that with inflation, and there's no need for a cat here. According to the chronological timeline you just witnessed, inflation occurred before the Big Bang. The inflaton field transformed from being an extremely tiny entity into something macroscopic and beyond imagination. Afterward, it and its fundamental particles decayed into pure energy, following the equation E equals mc squared. A tremendous amount of energy was released, making the universe incredibly hot. That's how the hot Big Bang began. In this scenario, the expansion rate of the universe during the inflation era was so extraordinary that all quantum fluctuations, oscillations that could happen, and indeed did, froze in place one after the other. What's even more remarkable is that these frozen fluctuations can still be seen today in the highly accurate image obtained by scientists from the relic radiation. Inflation predicted the incredible smoothness that fills the universe, the relic radiation. But that's not the only reason inflation was introduced. It also suggests that there should be quantum fluctuations imprinted on this background radiation as tiny temperature variations in different directions. These variations are called anisotropies. Surprisingly, such fluctuations were detected by American astrophysicists George Smoot and John Mather, who were awarded the Nobel Prize in Physics in 2006 for their experimental discovery of extraordinary homogeneity in relic radiation and the anisotropies it contained. These anisotropies are on the order of a thousandth of a degree Celsius. They are significant, even crucial, as they are believed to have led to the formation of stars and galaxies. Without them, the universe would have remained uniformly distributed, and stars would never have formed. So, inflation once again connects the microworld, the quantum realm, with the macroworld, from the earliest stages of the universe's development to the formation of the structures we see today. It even hints at what mysterious dark energy might be, as this anti-gravitational force could originate from the residual energy of the inflationary field. Inflation potentially explains many cosmic mysteries, so it should be taken very seriously. And now, since we've touched upon this topic, let's explore some intriguing consequences of this scenario. As it's understood today, the inflaton field cannot remain calm and be a one-time occurrence, present only at the birth of the universe. It's supposed to undergo quantum fluctuations, allowing it to jump on a local scale from one vacuum state to another. Typically, for fields you've seen so far, such a process results in the creation of particles that can jump from somewhere to somewhere else or spontaneously emerge from nowhere. Here, however, it means that the field can create a small universe from itself, over and over again, on various scales. When I say everywhere, I mean precisely that, although the time intervals can be vast or not. This process is called eternal inflation, and it never stops. Universes bubble up within already existing universes, where the quantum vacuum of the information field transitions to another state, a different vacuum. These bubbles are like droplets of oil on the surface of a lake. They grow and grow, and inside these bubbles, more universes bubble up within universes within universes. This is an example of a multiverse, but it's a different type of multiverse than what you've encountered so far. In this scenario, you and I would live in one of these universe bubbles, and there could very well be bubbles ready to emerge inside our spacetime at some point in the distant future. Just as our universe possibly emerged from another bubble that is much larger and maybe slightly damaged. Consequently, the potential demise of our observable universe due to a cooling off phase might serve as a template for the growth of new universe bubbles in the future. We will take another look at these intriguing, spontaneously appearing universes as you travel through the landscape of string theory at the end of the book. However, compared to what you're about to encounter in string theory, nothing will seem more normal to you, I assure you. You should even consider the universe bubbles you've just met as a prelude to the ultimate destination of your journey. But before we go there, before we return to the visible universe to see where these famous strings might hide, what they represent, and what they mean for our reality, let's try to look beyond the inflation era, using the knowledge we've gained for those who may wonder how the universe came to be. The personal inflation scenario might seem unsatisfactory because it lacks a true beginning. It's always bubbles. But there could be other possibilities. I won't list them all here, but I'll mention one, the Chapter 3 Universe Without Boundaries and Inflation. According to eternal inflation, an infinite number of universes have always existed, exist now, and will continue to be born, and our universe just happened to become ours. Now let's imagine a single universe with a single beginning, whatever that means, without an inflation epoch. Let's rewind time, starting from the Big Bang, boom. And before that, there was inflation. Let's take a look at it during this period. It's a dramatic collapse. But before that, we have problems, the Planck wall. The Planck epoch is where and when space and time cease to make sense. The Planck wall is about 380,000 years from the surface of the last scattering, at the end of the universe. We can make a reasonable guess about what comes after the Planck epoch, something we might call the zero moment of time. However, we don't allow ourselves to make such claims. We can't reach the zero moment of time within our universe, and we can't speak of time where or when it didn't exist. Talking about time before or prior to the Planck epoch is meaningless. This requires quantum gravity with entirely new concepts to replace space and time, a challenging task related to the search for the initial conditions of our reality. Stephen Hawking and American theoretical physicist James Hartle tackled this problem around 30 years ago. They were the first scientists to venture into this territory. Now, imagine a mini copy of yourself in a newborn universe, a universe where space and time are just beginning to have meaning. It's tiny, a bit larger than a bread box, but still small. You're inside it, and you're tiny, too. You can't see much. Everything that happens on scales smaller than the Planck length is beyond your sight. In this realm of extreme youth and near blindness, doesn't this situation remind you of scenarios you've encountered before, delving into the quantum world? Haven't you tried to become a yogi by closing your eyes to avoid interaction and accessing what's hidden from sight when studying the inner workings of atoms? To understand what's happening around you, you had to somehow become a yogi. To grasp what's discovered in this way, you learn that in the quantum world, when nature and cats are left unobserved, all quantum possibilities occur simultaneously. It's even worse here. You're facing visible chunks of particles. This is the past of our entire universe, concealed by the Planck wall that marks the birth of the known spacetime. The Planck wall now surrounds you, making it all inaccessible to your senses. So, according to the quantum law, the Planck wall hides a superposition of all quantum possibilities. What might you ask? Well, the possibilities of the past. In this very young universe, existing in its own right, following one rule of the quantum world that no one is watching, all possibilities can and do happen. Hawking applied this idea to a newborn universe, but he couldn't use the time we know and use every day. No one has the right to use it beyond the Planck measurement system. So Hawking turned it into something else, something more manipulable, a so-called imaginary time. With it, he examined all possible histories of the universe's past, the histories no one can see from the inside. The idea came to him in the 1980s, fresh from his discoveries about quantum black holes. He learned that black holes emit particles. He learned that quantum gravity must exist. Hawking's mind ventured beyond the Big Bang, along with his colleague, American theoretical physicist James Hartle from the University of California, Santa Barbara. Together, they wrote down a formula that forever changed how I perceive the universe. Hawking and Hartle postulated that all universes that led to our current universe must come from nothing, truly nothing, a mathematical nothing, not some finite something. A finite something a finite time ago, and they considered all universes with this property, and there were many of them. They obeyed the golden rule of the quantum world: when no one is looking, all possibilities can and do occur. This leads us to the golden rule. In young universes, still in their infancy, they have to follow this rule because no one is watching. All possibilities can occur and do occur. Hawking and Hartle, unlike Hawking's earlier work, had a hard time sifting through all these possibilities. There were so many of them. They obeyed the golden rule, not a golden rule to come. They took all these universes down on paper. This means that they added everything with a plus sign and claimed that their sums are what the universe was in the times before the Planck wall, where no one could look at it. Their mathematical formula is now known as the wave function of the universe, as Hawking and Hartle proposed. The initial condition stating that all possible states considered by the universe have arisen from nothing is called the no-boundary assumption. From their point of view, our universe, with all possible states as a young universe, had no beginning, and then it became ours after some finite time when space and time gained meaning. What exactly this means doesn't really matter here. The craziness is that they did it. They wrote down the mathematical initial conditions for the entire universe. They mathematically solved the problem of creating our universe from nothing. A few words of caution: this is not the end of the story. Practically tracing any calculations within these devised mathematical frameworks, like Hawking and Hartle's, is incredibly difficult, if not impossible. Nevertheless, by simply writing them down, they became the first humans to provide a mathematical formula for the origin and subsequent evolution of our reality. Previously inconceivable milestones for humanity. Humanity has been trying to decipher the laws of nature for thousands of years. Our understanding of these laws has evolved over time, and a century ago, Einstein introduced a new concept of gravity. We all started to realize that the past can be discovered not only beneath our feet through archaeological excavations, but also among the stars. Around the same time, many scientists began uncovering the strange quantum laws governing the microcosm. About 30 years ago, inspired by the results of black hole evaporation, Hartle and Hawking boldly started connecting all these pieces and developing a mathematical formula for the origin of everything. Of course, their vision could turn out to be deeply flawed in the future, just as any ideas that take us beyond experiments might. But that doesn't matter. What's important is that the question of the origin of our universe has entered a new era, where mathematical physics, at least, allows us to gather information about the subject. Although Hawking's idea of considering all possible universes using imaginary time did not come out of thin air, it is present in the works of some of the brightest minds of the 20th century, particularly Paul Dirac and Richard Feynman, who devised such a concept for creating modern quantum field theories. According to this scenario, the visible universe is still a sphere with a radius of about 13.8 billion light-years. This is the largest scale we can explore. Nonetheless, it's amusing to think that by collecting signals from space and venturing further into the megaverse, humanity may end up not only looking into the past, but also delving into the microcosm. Our ancestors didn't know this, and now you see the opposite could very well be true, and you're about to revisit the microcosm. But this time, you'll go deeper than before. Down there, you'll find a window opening into an entirely new reality, A reality larger than anything you've dreamed of so far. Even more bubbles within bubbles within bubbles. Eternal inflation in the grand view has revealed little in the small view, and now you'll discover something enormous. But where to look? Chapter 4, Uncharted Territory. As you now know, our entire visible universe is a sphere with a radius of 13.8 billion light-years. With such a gigantic perspective, at first, you see the threads of giant galaxy clusters, bathing in gases and dark matter. More importantly, quantum fields are present. Although you can't see them from such an enormous height, you can feel them. They include the Higgs field, which gives mass to everything that has mass. There are also inflatons, fields of dark energy that counteract gravity's influence, keeping the universe from expanding too rapidly. Gravity itself is here, shifting everything closer to everything else. You're watching from the side, beginning to zoom in. Now you see galaxies with hundreds of billions of stars, their supermassive central black holes spewing out jets of high-energy light and matter. You see the presence of dark matter, how it prevents galaxies from ripping apart due to their own rotation. Keep zooming in. You're at the scale of stars, massive balls of glowing plasma emitting light that we humans use to explore the distant universe. Planets follow. Spherical worlds too small to ever become stars. Then, asteroids and comets, living creatures hidden on our planet, kilometers of atmosphere, and then microbes, cells, molecules, electrons, and photons. Protons and neutrons, quarks and gluons. You continue to zoom in. You've returned to the territory of quantum fields. Gravity is already here, armed with all its quantum forces. Keep zooming in, and then stop. You remember what went wrong with quantum fields. You remember the normalization tricks used by quantum physicists to get rid of the troublesome infinities. And you remember that attempts to view gravity as a quantum field completely failed because the infinities that arise in this case cannot be removed by any means, resulting in the collapse of space-time throughout the entire universe. It's these infinities that we need to eliminate now, and behind them, you'll see a window leading to a grand new reality I mentioned at the end of the previous chapter. Soon, you will pass through it, but first, we must get rid of these pesky infinities. So how do we intend to do that? Well, let's see what we know about spacetime. We know that its description using 21st century physics has its boundaries, both in the mega-world. From some point after the Big Bang through the epoch of inflation when the universe underwent Planck scale conditions. This boundary is at 13.8 billion light-years from Earth in spacetime. Similarly, in the microworld, there are similar boundaries, and this happens everywhere you approach something. At some point, you must reach the Planck scale unless something prevents you from doing so. Thanks to Hawking's work on black holes, we know that gravity is not shielded from quantum effects, and quantum gravity, in some form, exists. Although we don't always understand what it might mean for reality within its territory. There are limits to what we can explore, whether in the mega or microworlds, and they are determined by the Planck scale. If you reach these limits in experiments, you won't find any difference in energy, size, or time in laboratory conditions. These boundaries have energies that are too small and speeds, as of today, are theoretical limits. What's even worse is that there's a practical limit that nobody can truly reach because the process would result in tiny Planck-sized black holes. I mentioned this at the end of the last section. To investigate reality beyond this boundary, you have no choice but to try to push quantum gravity or some new physics beyond the Planck scale using the best modern accelerators for elementary particles and observing the sky. Theoretical physicists believe they understand how nature behaves almost everywhere, from vast galactic scales down to the scale where all quantum fields merge into one. The energy required for this unification is about 1% of the Planck energy. Obviously, this is an enormous amount, equivalent to a temperature of about 100 billion degrees, but it's not the Planck limit. You probably remember that energy is related to size, and the higher the energy of a wave, the shorter the distances between its consecutive crests. The 1% of the Planck energy corresponds to the scale of the microworld and is about 100 times larger than the Planck length. This means there's untouched territory in reality, extending at least from 1 to 100 Planck lengths. From experiments, we know nothing about what happens there. A good way to imagine the significance of such an experimental gap is to think about what it would be like for a theoretical physicist to experience it. Imagine that you can only see the world with a resolution of 1 meter, which is much coarser than the thickness of a human hair. You wouldn't be able to distinguish any details in the environment. You wouldn't even see small children. They would suddenly appear as 100 meters tall. I'm not saying something might turn out to be children 100 times smaller than the Planck length, but we don't know what nature might hide there. And our reality roots somewhere in the microworld, from which it was created, in which it exists. Since no experiment has ever explored these scales precisely, it's possible that space and time start to differ from what we use somewhere before the Planck scale. It's also possible that gravity, matter, and light begin to change radically in this region. For example, maybe they all become one and the same. Up until now, you've seen mainly what's known. Now, you're going to explore what's unknown. And let's pretend that all of this is real so you can travel there. But keep in mind that this is pure theory. Nonetheless, some of the brightest scientists of our time have been working for decades to convey this picture to you. Chapter 5, String Theory. A strange blue haze of electricity surrounds the silhouette of your robot companion, as if the inner excitement has burst out of its electrons. You both float in space, surrounded by distant galaxies and far from the point where you narrowly escaped complete annihilation in a black hole. You've seen everything you needed to see, from the supersonic flight over to Lynn to witnessing the vacuum fluctuations of quantum fields and getting acquainted with matter and light. You've seen stars exploding to create new worlds, observed white dwarfs and black holes, which, in turn, hinted at the existence of the unknown. Now, it's time to continue the exploration, says the robot. Both of you start shrinking in size. You observe passing particles, the flickering of quantum fields, and continue to shrink until you reach the scale of the grand unified theory, where all three quantum fields are believed to behave as one. You keep getting smaller until you're far beyond the size of your miniaturized copies. You're squeezed billions upon billions of times smaller until you eventually reach the width of a human hair. At first, you don't see anything, but then you notice something ahead. It's a string. A string made of nothing, not even space-time. When you look at it, you get a sense that this oscillating object replaces both of these concepts. You haven't reached the Planck scale yet, and you can't quite grasp it in the theoretical way you're entering it now. There's no denying that everything you've seen so far above was not wrong. It's just that down here, none of the familiar concepts can be trusted, except for quantum theory. But it applies to strings as well as particles. What's oscillating right in front of you now may be one of the most fundamental elements of all. It's a quantum string. There's a chance that its existence could provide an explanation for everything you've seen before, including gravity and the existence of our entire universe. The quantum string vibrates before you, and you can't precisely determine its edges. You can't even say it exists as space-time does. When you look at it, it almost gives you the sensation that this oscillating object replaces both of those concepts. You haven't reached the Planck scale, and you can't quite grasp it in the theoretical way you're entering it now. But that doesn't mean what you've seen above was wrong. It's just that down here, none of the familiar concepts can be trusted, except for quantum theory. But it applies to strings as well as particles. What's oscillating right in front of you now may be one of the most fundamental elements of all. It's a quantum string. There's a chance that its existence could provide an explanation for everything you've seen before, including gravity and the existence of our entire universe. The quantum string vibrates before you, and you can't precisely determine its edges. You can't even say it exists as space-time does. When you look at it, it almost gives you the sensation that this oscillating object replaces both of those concepts. To the right, something else grabs your attention. You turn your tiny head to see another string, but it's different. It doesn't look like a guitar string. It resembles a closed loop, and it's vibrating in a quantum manner too. Its initial excitation isn't for light or gravitons, the carrier of gravitational interactions. This is about quantum gravity. This loop, this closed string, tells you that you're now traveling through the realm of quantum gravity. Imagine taking such a closed loop and placing it anywhere you like, and its vibrations would mimic gravity. You wouldn't encounter the lingering infinities that plagued quantum gravity before. They disappeared for good because you eliminated the notion that things happen at specific points in space-time, like particles moving in smooth space-time. Even though the quantum field theory has its quirks, it also says that when particles interact, it's not happening in a particular location at a specific time. The interaction occurs throughout the string. So, this closed loop, this string, carries gravity within it. It is gravity. And you have light emanating from open strings. Therefore, when taken together, they become theories that unify gravity and electromagnetism. Thus, quantum strings are more than just a quantum theory of gravity. A quantum theory of gravity simply deals with gravity in a quantum way, and it doesn't concern itself with other quantum fields. So, what about other fields? Can these strings be part of a theory of everything, a theory that unifies gravity and all the known quantum fields? To achieve this, you don't necessarily need to account for matter. You may wonder, what makes these strings so special? What's the peculiarity of their existence? Why do theorists find them so intriguing? You have these two types of strings, open and closed, and you can already discern quite a bit, but not everything. Let's go further, the robot declares, and both of you start shrinking even more. Now, compared to you, the open string is enormous. As you carefully examine it, you begin to see more than meets the eye. What you're about to undertake is something no person made of matter could ever do, but right now you can. Remember, when you venture beyond the known, you must be prepared to sacrifice something. Here, you must leave behind the special status of your universe, which you may have considered unique. From Newton to Einstein, you had to abandon the idea that the universe is static, that it has always been the same. You needed to acquaint yourself with space-time, its three spatial dimensions, and one time dimension, all intertwined into a unified whole encompassing matter and energy. To move from there to quantum field theories of gravity was a struggle. You had to turn all the fundamental theories into theories of open and closed strings. But that wouldn't be the challenging part. What you must give up here is the idea that reality consists solely of four dimensions. Strings don't exist in a four-dimensional space-time. They require more room. They live in a 10-dimensional universe. As you approach the string, together with the robot, you begin to notice that above all points you thought existed in our universe, 6 new spatial dimensions arise, constituting their own world. It's presumed that from these tiny extra dimensions, all the matter composing us emerges. If you find it challenging to fathom even 4 dimensions, let alone 10, don't worry. All you need to know is that 6 of them are tiny extensions in different directions beyond the usual left-right, up-down, forward-backward of our 3-dimensional world. They are too tiny to feel their existence or travel through them in real life. Now, as you and the robot have shrunk to such minuscule sizes that you can barely resemble anything, it's impossible to describe you. There are so many possible ways to add these extra dimensions, to create a string, so many ways to wrap these extra dimensions around themselves, each providing a different foundation for reality. Theoretical physicists have even guessed how many possibilities there might be, and the number has reached about 10,500. All of them have the potential to give rise to a universe, though not necessarily our universe. It's quite possible that all these possibilities exist at some stage inside bubbles created by eternal inflation, which you just heard about. But only a few of them could produce a universe where the laws of nature are compatible with the form of life we know. To exist as a human being, a specific set of extra-dimensional shapes had to be chosen. Otherwise, the laws of nature wouldn't allow it. How this selection happened, no one knows, except that it had to be made for you to exist here in our universe. This argument for selection is called the anthropic principle. It claims that out of the unimaginably many possible shapes of extra dimensions, only those compatible with the existence of humans should be considered. It's an attractive idea, and it becomes even better when you realize that instead of all dimensions remaining tiny, one or more of these extra dimensions could be large. "Follow me," says the robot, signaling you to follow. "We may never see this again," he adds. Now, something extraordinary is happening. You were always taught that you couldn't look at the universe from the outside, so discussing edges or boundaries was nonsense. However, it seems that you are now witnessing something that appears to be the edges. They are beyond the limits of what ordinary sensory organs can perceive. From the outside, you see your entire universe in another dimension. You see that open strings, those little strings, and their vibrations give rise to light. Now, they vibrate differently depending on the hidden dimensions in which they exist. And you also see that at the end of all these open strings, they are attached to our universe, which you just left. Meanwhile, the closed strings, the ones vibrating like gravity, can freely move outward, exiting the universe. Feeling something behind you, you turn around in amazement and find another universe parallel to yours. That's right, it's parallel to ours, and you see closed strings moving from one universe to the other, demonstrating that they can communicate through gravity. This is the fourth type of parallel universe, the most impressive of them all, called brands. It sounds like membranes, but without the M to signify they have more than two spatial dimensions. What you see before you is one such brand, another universe. There can be many of them, varying in size, and they can transform into each other, behaving like strings when physicists and mathematicians change the way they interact with each other. They can either be separate objects or different aspects of the same reality, viewed from different perspectives. All of this can be one aspect of a greater reality, regardless of what that may mean in this case. Some scientists, led by the brilliant Argentine theoretical physicist Juan Maldacena, have even shown that all of this could be understood without gravity. And each individual universe here could be imagined because something happens at its boundaries. As this truth dawns upon you, you find yourself beyond the universe. Everywhere and around, there are other universes with different sets of dimensions, and there are tiny spatial dimensions where strings wrap around themselves, causing them to vibrate into matter and light, forbidden from crossing their brand, their universe. You notice that some amount of energy can leave your universe. You even see what you believe could be black holes connecting neighboring brands through twisted, tubular, space-time distortions via gravity. Could there be other beings in these brands? Could black holes serve as gateways between your world and theirs? Can the singularity you haven't reached open access to another reality? Could the birth of our brand and our space-time be linked to collisions with other brands that existed before? Can dark matter and dark energy be explained by the existence of brands? Looking back at the universe you just left, suddenly you notice that something has changed over time, and you see bubbles of new inflationary universes appearing everywhere within your universe. Within your brand, spreading within what used to be your world like oil drops on the surface of a lake. "We need to go back," you shout. But the robot is nowhere to be seen, and you slip back into the nearest brand, hoping it's the one you came from, and you start growing again. The other brands become invisible once more, and the strings that can create your reality disappear in the distance. Now, around you, there are quarks and gluons, then protons, electrons, atoms, molecules, dust, sand, the sea. You open your eyes. You are on your deserted beach, in the same spot where you began your journey. Stars shine in the night sky, and a gentle breeze carries the scent of exotic flowers. Your friends are there, smiling. "He's awake," says one of them. "Pour him a drink," another says. A glass appears in the sand. You feel your head. It still hurts. You take a sip to clear your mind. You look around. Your coffee is still there. "I'm okay," you say out loud. But you pick up your phone and call your cousin's grandmother, just to be sure. Then, you are back in Margaritaville. Epilogue. Throughout history, philosophers, and now theoretical physicists, have tried to imagine a picture of the world to decipher its laws, the laws of nature, the existence of which is evident to all of us. At night, the language remained hidden for a very long time. They imagined themselves in impossible physical or experimental situations, and these experiments were called thought experiments, experiments of pure reason. Exactly this sequence of thought experiments you experienced in this book has allowed you to travel with just your thoughts across the known universe and beyond. In Chapter 1, Jer used this method to demonstrate how bizarre quantum rules should emerge when not bound by macroscopic everyday events. He ended up with Schrödinger's cat, which turned out to be neither alive nor dead but both at the same time, seemingly strange things. But upon closer examination, it turned out that even Einstein drew many benefits from his thought experiments. He imagined what reality would look like if the speed of light had a fixed limit. To do this, he descended to the level of a photon and looked at the world from there. In his mind, the special theory of relativity was born, talking about how an airplane flying at the same speed as yours would ultimately end up 400 years ahead in the future. Subsequently, it was proven that this was indeed the case, intuition, though not grounded in common sense, guiding humanity's discoveries for over a century. As Einstein famously said, imagination is more important than knowledge. The faces you saw in the starry sky just after waking up on the beach were the giants of thought from the past and the present. Of course, I can't name them all. There are too many. Yet, those individuals, with every passing minute, have created the history of humankind, page by page. They wrote a book about what we know at this moment about our reality. Most of them remain unknown to the wider public, but their contributions continue to make our world better. Known pains, extensive with each passing minute, they created the history of humankind, page by page. They wrote a book about what we know at this moment about our reality. Most of them remain unknown to the wider public, but their contributions continue to make our world better. You've witnessed that there are countless other planets and worlds in space that may someday make contact with us. Regarding today's knowledge, it's impossible to move from one part of the universe to another within 1 or even 1,000 lifetimes. You can only do this in your mind. But just a few generations ago, it would have taken several months to sail from Europe to Australia. Now, it only takes a few hours by flight. We don't know what tomorrow's technology will make possible. We don't know what will one day allow us to realize the theory of everything. Today, as I mentioned earlier, it gave us GPS, and tomorrow it might enable us to find the shortest path in space-time, like wormholes or burrows that could connect two distant places without the need to traverse the vast space in between. Until now, humanity has sent people to the moon, and we have sent robots to the boundaries of the solar system. What lies beyond it, humanity has seen but not ventured there. And you have explored all known and unknown series of thought experiments, thanks to these flights of thought. You've brought together all the knowledge of theoretical physics from the beginning of the 21st century. Some of what you learned during these journeys may turn out to be false: dark matter, dark energy, parallel worlds, and realities. All of these are ideas that scientists may eventually discard. Nevertheless, they are the most powerful ideas of our time, reflecting how humanity is trying to make sense of our universe. In a few centuries, all of this may be discarded or embraced. We don't know. But living today means being surrounded by these extraordinary ideas. So, before I allow you to see everything from your own perspective, here's a final summary of what you've seen, plus a little extra. As you know, he did not discover the theory of everything, the so-called elusive theory of everything I mentioned some time ago. Nor did he explain the strange orbit of Mercury, let alone the expansion of space-time. So, in a sense, his theory is wrong. However, it's brilliantly wrong. We know where it works, and we know where and why it falls apart. We are allowed to use it within the approximate scales that our human brains can grasp, somewhere between the mega and micro worlds. At excessively high speeds and energies in these worlds, Newton's laws become meaningless, and our senses do not help. But surprisingly, humanity has managed to decipher the laws of nature, even where we cannot see them. Quantum field theory is used in the microworld, and general relativity takes care of the mega-world. Between these two worlds, Newton is the king. Where Newton's theories fail to work, strange new phenomena are expected to emerge, hinting at new mysterious realities that border our own. Both quantum field theory and the general theory of relativity have opened our eyes and minds to a universe much more extensive than anyone from our ancestors could have ever imagined. However, to this day, these theories also have limitations. But unlike Newton's theory, no one knows for sure what lies beyond their boundaries. In this book, you embarked on a journey through these highly successful theories, and in the last part, you took a timid step beyond their limits. You entered a universe whose fundamental components are hidden, a universe created from numerous realities and quantum possibilities, leading to strange laws in universes that are not our own. Einstein's extraordinary vision was to understand that gravity was not what Newton thought it to be. Einstein showed that it curves and warps. Gravity, matter, and energy are connected in a very simple way. Our universe has what we call space-time, curved shapes that are determined by its contents. The effect of these curves on nearby objects and light is what we perceive as gravity. This is the essence of the general theory of relativity. It took 100 years to figure out the local shape of the universe beyond the stars and how gravity affects surrounding objects. To do that, you simply need to know the energy contained within a star. Many scientists did these calculations, starting with the German physicist Karl Schwarzschild in 1915, the same year Einstein published his theory. Schwarzschild worked out the exact geometry of spacetime outside a star. He was 43 at the time and achieved success during his service on the Russo-German front during World War I. He died a few months later from a disease he caught there. The war claimed too many lives, including those who, like Schwarzschild, could have helped us understand the world better and faster. Schwarzschild's pursuit allowed us to speculate on how objects move around stars and light. He calculated the correct orbit of Mercury and showed that it had to deviate from the Sun. In 1919, an expedition led by British astronomer Sir Arthur Eddington observed noticeable deviations in photographs taken during a total solar eclipse that year. The stars near the Sun appeared to be in a different position than they should have been. This matched Einstein's predictions. The light from these stars appeared to bend due to the Sun's influence on spacetime. Light itself was affected by gravity. Soon after Schwarzschild's death, the same mechanism was applied to larger objects, galaxies. It predicted strange cosmic mirages, arcs, or light rings floating around the centers of distant galaxies. These were images of even more distant galaxies whose light was distorted on its way to us. Galaxies acted as cosmic lenses, allowing us to see even farther and deeper into the history of our universe. Such lensing mirages were discovered more than 60 years after Einstein's work, in 1979. Now, they can be seen on almost every image of deep space obtained with telescopes. I'm not showing that Einstein's geometric interpretation of gravity works not just in the immediate vicinity of the Sun, but throughout the entire cosmic space. The general theory of relativity has given us a new perspective on the universe. You and everything are surrounded by all the information reaching us now from the past. We are at the center of our visible reality, and everything in this reality follows Einstein's laws, including the inner content of black holes. The same applies to our understanding of matter and light. The entire visible universe is governed by the same laws that apply in our cosmic neighborhood. The matter we are made of, the light reflecting off our skin, all of it adheres to the same quantum laws that govern the visible universe everywhere. The unification of the laws of distant galaxies and nearby galaxies led to the discovery that our universe has a history. In its past, it underwent a Big Bang. The past cosmic epochs can be read in the stars, all the way to the point where light ceased to travel freely. This moment, this place in the past of the universe, when space became extensive enough for light to move freely, is called the surface of last scattering. What remains of the temperature emitted by it is called the cosmic microwave background or relic radiation. It carries imprints of what existed before. Apart from this past, observations of the night sky can only lead to indirect conclusions about what once was. Someday, we may use light-independent sensors, working, for example, on gravitational waves, and then we will have the ability to directly receive more distant signals. But we are not yet at that level of development. Until then, we need to recreate the conditions that once existed everywhere in the extremely tiny volume that our universe was limited to. To understand what happened starting from the 1970s, particle accelerators are working on precisely this and have not led us to an unprecedented level of confidence in the theories used to explore the world of particles. The particle of light, quantum field theory, gave us a realistic picture of what the universe was made of and exists as, down to a billionth of a billionth of a billionth of a second after the presumed birth of known space and time, the birth and existence of which Einstein's general theory of relativity predicted. In the 1970s, we learned that the general theory of relativity has limitations, that there are boundaries to what it can achieve, and in places and calculations, a new theory of quantum gravity is needed, among other things. What this theory will consist of, we do not yet know, but we know that it must exist. Black hole evaporation hints at its existence, diminishing in size to find the possible location of future theories. You have ultimately entered a completely new reality, a reality consisting of strings, brands, and additional dimensions. It was a step into string theory, perhaps as popular as quantum gravity theory or the theory of everything, although it is still expected to make testable predictions. Among these theories, string and brand theories, sometimes called M-theories, the robot has completed its mission, coursing through space-time and beyond. Since you have reached a place where even the most powerful supercomputers invented by humanity are powerless to penetrate, only the human mind can go there. Now, you can finally find out everything you want to know about the world where you live. Or do you have doubts that theoretical and experimental inventions that have gone beyond today's knowledge are forthcoming? Inventions that open new windows into a universe far more vast than anyone currently alive can imagine. General theory of relativity and quantum field theory may eventually become as perfect as Newton's theory. To do this, we need to know why and where they fail, what their shortcomings are now. However, they are wrong in the same way that Newton was wrong. Thanks to these mistakes, we can peer into the unknown. Without Newton, without a template for comparison, we would not even notice a slight deviation in Mercury's orbit. Without Einstein's equations, we would remain completely ignorant of what the universe has in terms of history. we would not have built a picture of how the universe works as a whole. Without this picture, we would not have detected dark matter and dark energy either. Mistakes are needed to find the right path to move forward. I hope that the next time you look at the stars and the moon, you will remember how mysteriously vast and beautiful our universe is. Because only by expanding our collective knowledge, by dreaming and hunting for its hidden beauty and secrets, will we find the path to the long-term survival of the human race.